PSC 132 on-demand resources. If you're watching this right now and being like, Mike, do you really need an introduction for this? Then you have exactly the right attitude. So I really want you to make this on your own. I want you to skip around a bit. Only take what you need from this. I've made this like way more in-depth than it needs to be. I've made it cover things that like you probably already know. And I just don't want you to waste time studying things you already know. But if you're about to skip ahead, please, if you're going to do the quizzes, you can use these extra 3 pieces of information. They weren't included in the questions. They should have been. So you can use a water pressure temperature diagram, phase diagram. You can use your equation of state constant for oxygen of this, and the molecular weight of air. So if you do want an introduction here, if you're not sure what you know, then just try the quizzes. There'll be good review. If you're unstuck, or if you're stuck or unsure, then move to the next section and eventually check your answers using the annotated notes. So using my annotated solutions. Then, let's say you did really well on acids and bases and thermodynamics, but you're like, I need some practice with phases. Only watch the phase videos. Don't watch stuff that you already did well on. When you're doing it, skip around in the video and pause the video to try the practice questions. If I get to a point where you're like, oh, okay, now I know what to do, well then do it. Like pause the video again and do that thing that you now know to do. Then retry the quiz, at least the parts that you were hazy on, and then look at the entire solutions. And if things are still not working out for you, then watch that quiz video, and hopefully it will make sure that you come out on top. I wish you the absolute best of luck with all this. Talk to you soon. Equilibrium quiz time, let's go. This question really comes out swinging. It asks for this temperature at this equilibrium constant, some amount, a known amount, you don't know it, but someone knows how much HI was placed in this flask, and we need to figure that out because they're not telling us. We are told that at equilibrium there is that. So that much H2. So let's set up a little ice table up at the top here. So we have some amount of HI. Again, they're not telling us. And we don't have any of the other two. We're going to be forming some H2 and I2. And we're going to be losing that same amount times 2 of HI. Our equilibrium then is going to be X, and negative 2X. However, we know the value of X. They give it to us. So then, when we sub these in to our equilibrium expression, HI squared over H2 and I2, what we come out with, and let's fill that in there. Great. Sorry to anybody who was yelling at the monitor when I made that mistake. Okay, so we're going to come out with our K, which is given to us, 51.50. We have the concentration, the equilibrium concentration of HI is going to be the initial concentration of HI minus 2X. So minus 2 times our X value. I want to be really clear here. This is the initial amount of HI. All right, this is all going to be over 0.218. And we have 2 of those multiplying together, so let's square that. And let's not forget the square up top. Okay, so can we use a small x approximation here? Nope, we definitely can't. When we crunch this out, what do we come out with? We come out with 51.40. Actually, I'm going to jump right to the final quadratic here. 0 equals the initial concentration of HI squared. All right, and then we're going to have minus 0.872 times the concentration of HI minus 2.25. Bit of a pain for a multiple choice question, no? But anyway, when we do the quadratic, we come out with the concentration of HI being 2. Could be negative 1.13, but of course negative ones are not physical. And as a result, B is our best answer here. All right, now let's look at question 2. Please refer to these as we fill in the blanks. Okay, we have reaction 1. It has a medium K. Reaction 2 has a tiny k. Reaction 3 has an infinite K. All right. And then we've got a bunch of charts about products. Okay. So chart something represents the concentration of species at equilibrium for reaction 1. Well, for reaction 1, we have a medium amount, a medium K. So it's not going to be a landslide. It's not going to be 1 or 2. Or it's not even going to be 3, probably. So let's just check and make sure that this makes sense for chart 4. Chart 4 has some products and a reactant here. So what do we call that? Want to call that 0.5? 0.4? 0.5? Call it that. 0.4 squared over the reactant. Call that, say, I don't know, 0.7, 0.8. And when we crunch that out, we get 0.2, which, yeah, considering we're eyeballing stuff, looks pretty good. So I'm convinced that chart 4 gives us reaction 1. Looking at reaction 2, that was the one with the small value here, so this is going to be very strongly reactant favored. Okay, so is this going to be, let's see, is it going to be 1 or, nope, definitely not 2, 1 or 3 here, because both of these are going to be very strongly reactant favored. Well, assuming that we just started out with the same, with some solid here, we should have twice as much IO3 minus, twice as much IO3 minus. That kind of looks similar for both of these. Looks like both of them have twice as much of one product compared to the other. So we can just try this. We can be like, okay, this is about 0.9. And any 2's we should care about? Yes, there's a 2 on there. So call that 0.3. And call this one, I guess, 0.15. And let's just see if we get anywhere close here. We get 0.05, which is nowhere near small enough for reaction 2. So it's definitely not going to be chart 1. And if we did the same thing here, we don't need to do that mathematically. We can probably just say that those numbers are way, way, way smaller. And that's exactly what we need. So chart 3 corresponds to reaction 2. All right, looking good. Then for reaction 3, this thing is infinite, so it's all product. That's a nice easy one. The only one that is all product is chart 2. D, circle the chart that represents an insoluble salt. Well, an insoluble salt is one that does not dissolve very much. As a result, the one that is the least product facing is going to be the insoluble salt, so we're going to circle chart 3. All right, let's continue on now. And we're given a bunch of other reactions here. They ask us, determine the value of the equilibrium constant Kf for the soluble complex. Okay, the PbI2. Okay, so let's find this PbI42 minus. We find it there, and we find it there. Oh, and we're just looking for this, this final reaction here. Okay, so this K is looking pretty good. The only place in our component reactions that we have PbI4 minus is in that second reaction. So we know we need to keep it on the product side and with a stoichiometric coefficient of 1. We're going to need to, however, flip this one and maybe not. If we flip it, then we get the iodides on the same side, and it would add up to 4 iodides. Let's just make sure. We need to cancel the lead 2s. So yeah, if we flip it, it's going to cancel. So our Kf is going to be 1 over the Ksp times K. That's going to be 1 over 7.9 times 10 to the negative 9 times 2.37 times 10 to the negative 4. Fantastic. And that is going to come out to about 3 times 10 to the 4. A is our best answer here. All right, let's continue on for the last question. A reaction vessel is prepared by putting that much H2S and that much, oh goodness, NH3 into a sealed vessel. At least it's 1 liter. That'll make our math easy. Oh, it already contains that much ammonium hydrosulfide. Based on the reaction below, will there be a change in the amounts of these things after waiting some time? So based on our K, we need to know that our K is the reaction's home, the equilibrium's home. And equilibriums always want to go home. So we need to figure out where the equilibrium currently is. To find out where it is, we use Q, and we use our concentration. Since this is 1 liter, all of our moles are also molar, so we can just sub in the moles as if they were concentrations. So that's nice. We have concentration of H2S, NH3, and oh, that's a solid. That does not go in our Q. All right, so our Q is equal to H2S was 0.2 times 0.05. And when we crunch that out, we get 0.01. Then we consider our number line. K is always in the middle. It's 0.11. And where is 0.01? Well, that is less than K. And what that means is that the reaction must proceed to the right. Okay. So now we can evaluate our answer choices. The amount of the solid will increase. Nope, it's going to decrease because the reaction is going to the right. It's going to decrease. I like B. The amount of will stay the same. Nope, we are not at equilibrium. And we can figure this out using the method that we just described. So B is our best answer for question 4. I hope this was helpful. Good luck on the rest of your studying. Just a quick quiz for KSP, or at least one question. This question turns out to be fairly lengthy. They tell us we have some solution containing lead 2+ at this concentration and silver plus at this concentration. We add this thing, and that's going to react with both of these. But it's not going to react with both of these at an equal rate or at an equal equilibrium. It's going to prefer to react with one over another. They tell us the KSPs for these. What do these mean? Well, the lower the KSP, the less soluble the species is. And in this case, the earlier it will precipitate. So looking at these, we see that the KSP for our lead version is about 100 times less than for the silver version. Now we do actually have even a little bit more lead in here. So absolutely, we are going to be having our lead precipitate first here. Okay, so now let's read this question a little bit carefully and make sure that we're answering exactly what it's asking. What fraction of the first metal, so that's going to be lead, remains in the solution at the moment when the other chromate begins to precipitate first? So that's a tricky conceptual idea. How can we represent that mathematically? When does something actually start to precipitate? Right on the threshold, it's going to be when the ions and solid are at equilibrium. In other words, this is going to be when Q is equal to K. And this is right when there are like practically no ions. Sorry, practically no solid. There we go. Okay, so what are we going to do here? We're going to use the silver chromate and find out exactly when Q is equal to K. Because that is when this precipitation is going to just begin. Okay, so our Q is equal to K, which is equal to the concentration of our ions. Oops, we're using silver here. Times, what are we making? Silver to chromate. And I guess this will be 2 minus. And as usual, be very, very careful here. That needs a square, because what's the reaction going to look like? I'll put that off to the side here. Let's write it as a KSP. So very importantly, it's going to have that 2 out front. All right, so now that allows us to do this calculation. We're going to be solving for the chromate concentration here, because we have our K. Our K is, for silver here, 1.12 times 10 to the negative 12. We don't know our chromate. Oh, and let's make sure that we square that. Wrote this out a little funny. Let's try that again. Our K is 1.12 times 10 to the negative 12. Our concentration of silver, that's going to be, there we go. I fixed a problem that was in my notes, and now we're back into business here. So our concentration of silver plus, that's what we're starting with. So it's going to be 0.005, and make sure you remember to square that thing. The concentration of chromate, that's what we're looking for. And that concentration of chromate comes out to be 4.48 times 10 to the negative 8 molar. Okay, and let's make sure we know exactly what we're talking about here. This is the concentration of chromate when the second one, when silver chromate just starts to form. We could alternatively say when it's just about to start to form, same deal. So then our follow-up question is, what concentration of lead 2+ exists at that concentration of chromate? So we're going to do the same type of thing. We're going to use our equilibrium constants here, but this time for lead. So for lead, this is a nice one-to-one reaction, so I'm not going to write out the reaction here. We're going to have our K is equal to concentration of lead 2+ times concentration of chromate. We know those two. So now we sub in values, 1.8 times 10 to the negative 14. We're looking for the concentration of lead. And in fact, I'm going to call this the equilibrium concentration of lead rather than the initial concentration of lead. Just don't want to get those two confused. And the concentration of chromate is the value we just found. So our concentration of lead 2+ turns out to be 4.018 times 10 to the negative 7 molar. And again, that is specifically the equilibrium concentration of lead 2+. Now, is that answering the question? No, not yet. Our question is, what fraction exists at this point? So if we want our fraction, that's going to be equal to the amount of lead at equilibrium over the initial amount of lead, 2+. So that's going to be 4.018 times 10 to the negative 7 divided by, what was it, 0.01? 0.01. And then, of course, that comes out to be 4.018 times 10 to the negative 5. Oop, and not molar anymore. This is a ratio. So that is our final answer. Whew. Tough type of question, but I've seen some tough questions on the midterm, so I could totally see this kind of thing happening on your exam. Hopefully this was helpful. Good luck on the rest of your studying. All right, it's acid-base quiz time. First question talks about this reaction. They say it's a consider the Bronsted-Lowry definition here. And which one is the acid? The acid is the one that's going to be giving up a proton. So if we look at our nitrogen part in both sides, we see that this nitrogen has gained a proton. So it's not giving up a proton. And as a result, H2S is our acid, and the NH3 must be the base. What is this thing called? This is called a salt. Looking now at question 2. Solution made up of that is 4.1% dissociated. Which of these is going to increase the percent dissociation? So this seems a little bit tricky. Let's write out the reaction first. So we have HA, that's some aqueous thing, plus H2O, that's some liquid. It's at equilibrium with H3O plus aqueous and A minus also aqueous. So let's try to use Le Chatelier's principle to consider each of these things. If we add HCl, what's that going to be doing? That's going to be adding H3O plus and chloride, but we don't actually care about chloride. And if it's adding H3O plus, it's going to be increasing the concentration of a product, shifting the reaction to the left. So that is not going to increase the dissociation, that is going to decrease the dissociation, and A is out. Looking at B, adding 200 mils of water. Well, what's that going to do? It's going to change all our concentrations, right? It's going to specifically decrease all concentrations. So if it decreases all of our concentrations, there we go. But this decrease in concentration is not just going to come out in a wash. If we decrease all of these concentrations, and in fact, let's make this really explicit here by writing out our K, in this case a Ka. If we decrease all these concentrations by the same amount, that seems like it's going to have no effect, or it seems like it's going to affect Ka. But we know that Ka cannot be affected by changes in concentrations. So what this means is that this is going to actually have a net impact. It means that we're going to have these decreases in concentrations. They must necessarily be a little bit smaller. And this decrease in concentration is going to necessarily be a little bit bigger in order to keep this Ka the same. I know I put a negative sign there. Let's get rid of that. So what does this mean? It means that on the whole, this reaction is going to be shifting to the right. That is going to increase the dissociation of HA, so B is a correct answer. C and D are, I think, a little bit easier to deal with, especially C. If you increase the concentration of a reactant, is that going to shift this to the right? Well, it is, but you've also added more reactant. And the shift with Le Chatelier's principle is never going to be enough to completely overcome what you've added there. So that would actually be decreasing the dissociation constant. And then decreasing the temperature, that's kind of a weak answer. Generally speaking, well, we want to pick B because we know B is true. D could be true. Empirically, it's not. But we can prove that B is true, which makes B a much better answer for this question. All right, now let's move on to question 3. Question 3 is an absolute classic and one that you will want to be prepared for. It asks us for the pH of solution of sodium fluoride given this concentration. So this is, as I said, an absolute classic. We got to think about what is actually going on here. In fact, we can take this down to a 50-50 right away. Sodium fluoride would break up into sodium plus and fluorine minus, or fluoride. Sodium plus is that conjugate of a strong species and therefore does not contribute to the pH of solution. We can happily ignore sodium plus. But fluoride, that is a weak base. And if we were unsure about that, they tell us the Ka for HF. So it would be HF plus water goes to and returns from H3O plus and F minus. Now, since HF is not a strong acid, that means that F minus is a weak acid and is going to contribute to the pH of solution. But we're not starting with HF here, we're starting with F minus. So the reaction for F minus is going to be also reacting with water. And that's going to give us our HF plus OH minus. We need some kind of equilibrium constant in order to help us find the equilibrium concentration of OH minus. And if we need an equilibrium constant, we're of course going to be drawn to this Ka. But this Ka is the acid constant for HF. We need the base constant for F minus. Do you remember how to do that conversion? It's Ka times Kb equals 10 to the negative 14. All right. Oh, and actually, I said we'd take it down to a 50-50. Let's actually do that. The F minus is a base, and as a result, we should be expecting a basic pH. A basic pH is one that is greater than 7, and that allows us to immediately eliminate two of these answer choices. And this question is long enough that it's quite nice to have it down to a 50-50 in a worst case scenario. Okay, now we can find this Kb. That's going to be 10 to the negative 14 over 6.8 times 10 to the negative 4. And when we do that, we come out with 1.5 times 10 to the negative 11. It is a pretty small number, and we should be expecting that F minus is a pretty weak base. And as a result, we should probably be expecting that this is going to be pretty close to neutral. Based on that, we might be able to select C, but let's follow this question through, because who wants to ride on intuitions like that? So now what we need to do is we need to figure out what the equilibrium concentration of OH is going to be. We don't even know what the equilibrium concentration of F minus is going to be. All we know right now are the initial concentrations. Does this ring any bells? We're going to set up an ICE table. So initial concentration, change in concentration, and equilibrium concentration. As usual, you can do this for either molar or moles. Since here we don't even have a volume, I'm not tempted at all to try to do this in moles. Our initial concentration of F minus is this, 0.10. We don't actually care about the water because that's not appearing in our equilibrium constant. Water would be a liquid. F minus, or HF, not starting with any of that, and you're not starting with any of your products. So the change is going to be a nice easy plus x, or negative x plus x plus x, because these are all one-to-one. That gives us 0.10 minus x for our equilibrium concentration of fluoride. And for HF and OH minus, we calculate this to be a very easy calculation, couple x's. Okay, we're like halfway there. Now what we're going to do is we're going to use our Kb that we calculated, and we're going to say that that's equal to our concentrations of products over concentrations of reactants. We've got that. And now we sub in our equilibrium concentrations to our Kb. While I'm at it, I'm also going to sub in my Kb value that I found before. My concentrations then are going to be x and x over 0.10 minus x. Okay, now this would be a little bit annoying. We'd have to do a quadratic. But do we really need to do a quadratic? No, absolutely not. This x is very, very, very small. And as a result, 0.1 minus this very, very small number is going to be approximately 0.1, at least to the significant figures that we have here. If we wanted to do this quantitatively, what we would do would be taking our F minus over our K. Which K? Kb. And we're going to ask ourselves, is this a big number? So let's find this thing. we're going to have 0.10 over 1.5 times 10 to the negative 11. And that's going to come out to be 7 times 10 to the positive 9. That is a gigantic number. That is well above any of the thresholds we might have seen. So yeah, this is gigantic. Normally the thresholds are somewhere between 100 and 1,000, depending on the year. But yeah, not even close. And normally they're not going to give you anything close because the 100 to 1,000 are kind of arbitrary decisions anyway. Another way to think about this is that this is a multiple choice question. If we're off by 0.1, who cares? We just pick the closest answer. All right, so now we're going to have our 1.5 times 10 to the negative 11 equals x squared over 0.10. And we can solve for x here, and when we do, we get 1.2 times 10 to the negative 6 molar. Okay, but what is that molar of? Like, it's so easy to get lost on these questions. It's molar of hydroxide. HF too, but we don't actually care about HF. We're looking for the pH. So I'm just going to put that there as a reminder. And that allows us to find the pOH. pOH is going to be negative log of the concentration of OH minus. So that's negative log of 1.6, 1.2 times 10 to the negative 6. As a result, we're going to come out with 5.92. And at this point, you could see that if you had not done that initial consideration, you might have been tempted to pick answer choice B. They know that that is an intermediate step, and they've got an answer choice waiting for you. They're not asking for the pOH, though. They're asking for the pH, so we need to make that conversion. This 14 is the pKw of water, and it's usually given to us. So we're going to have then pH equals 14.00 minus the pOH. And that's going to come out to be 8.08. Whew! C is our best answer for question 3. All right, let's continue on. And now we're in our knowledge development questions. We have 200 mils of this is mixed with 200 mils of this, and we want to figure out which ions are present in significant amounts. Our first step is going to be to find the number of moles of each of these things, because it's not concentrations that react, it's not volumes that react, it's moles that react. Our moles of HCl are going to be C times V equals concentration of 1.0 molar, just 1 molar. They're being a little bit lazy here. 1 molar times 0.200 liters, and that's going to come out to be 0.2 moles. If we do the same thing with sodium hydroxide, we're going to come out with 0.5 times 200. That's going to give us 0.1 moles. So based on that, what reaction is going to be occurring here? We're going to have HCl plus sodium hydroxide. And these are both strong species, so this is going to be a unidirectional reaction forming our products. So we're going to have H2O plus, and we could either write this out as sodium plus and chloride minus, or as sodium chloride. I like writing it out separately personally. Okay, and does this completely use up everything? No. We're going to have some HCl left. And if we want to be more specific, well, we can do that subtraction. We're going to say that we have 0.1 mole of HCl left. Okay, so what are the ions that we have? The most important one is that we're still going to have a lot of H3O+. We have a strong acid in solution. We still have a fair bit of it left, so we are absolutely going to have H3O+. The other ones that don't matter as much are we're going to have sodium plus and chloride minus, because we have those just as counter ions. Importantly, we are not going to have appreciable amounts of hydroxide left. Some sodium, yes, but no hydroxide. They ask us to calculate the concentrations of these ions. Okay, so we kind of qualitatively talked through an ice table a second ago, but now we're going to do it for realsies. So this is question 2. I'm doing this all in moles, and I'm doing that because I bothered to calculate it before, and also the volume here is going to be changing. We're going from 200 mils of two different things to 400 mils total, so that's going to be something I'm going to have to consider. Our initial number of moles, as we calculated before, was 0.2. For sodium hydroxide, 0.1. Don't need to put units there because I've got them in my headers. We don't care about water. And frankly, we don't really care about these either, because these are not going to contribute to the pH of solution, but they did ask us to find all the concentrations, so we might as well. We're starting out with 0 of those, and how much of these things are going to be changing? We're going to be losing 0.1 mole of everything. So, minus 0.1, minus 0.1, and then we're going to be adding 0.1 of both of these. So what do we come out with? A bunch of 0.1s for our products. We come out with 0.1 for our equilibrium concentration of hydrochloric acid, and 0 of our sodium hydroxide. So now we can answer this question fully and just say we're going to have weight. They're not asking for the number of moles, they're asking for the concentrations. So what do we need to do? Really, as long as you remember that step, it's probably not too bad a step. 0.1 moles over the new volume, which is 0.4000. Great. And we're going to come out with 0.25 molar. So that is going to be the concentration for all of these ions. Finally, we can do question 3. We're estimating the pH. pH equals negative log of the concentration of H3O+. That's going to be negative log of 0.25, and that comes out to be 0.60. All right, fun. Let's continue on, and let's look at this one. What is the pH of a solution that contains this much hypochlorous acid and this much of its conjugate base? They give us the reaction. So let's treat this as question number 1 and this as question number 2. This is the kind of question that I am most expecting you to see on your final exam. You weren't tested on buffers on your midterm this semester. So this kind of makes me think that you're going to get tested on buffers on the exam. It's hard to escape this course without getting tested on buffers. Okay, so with number 1 here, we're going to use our Henderson-Hasselbalch equation. We're going to use the pH equals pKa plus log of the base, I'll call this A minus, over the acid, I'll call this HA. And depending on the year, I have seen this with a negative sign here and this flipped. If that's the case, that's totally fine. If they're mathematically identical, so use whichever one you prefer. Our pKa is 7.4, and we're adding log of 0.1 for the base, and 0.25 for the acid. And that's just straight up algebra there, so 7.00. Life is looking good. We should also just make sure, does this make sense? It does make sense because we have more acid than base. And as a result, the final answer should be more acidic than our pKa. That is what we found, so fantastic. Now let's do 2. Now this is a little bit dicey because really they should have specified some kind of volume here. In order to make this question actually doable and also interesting at all, I'm going to say assume a total volume of 100 mils. That allows us to find the number of moles of our HClO and our ClO minus. As usual, it's just CV, and we're going to be using that as our volume. So we have 0.25 times 0.1, so we're going to get 0.025 here. That's a number of moles. And for ClO minus, same type of deal, but now we're going to get 0.010. These are our initial, oops, I'm a little cut off there, aren't I? Our initial numbers of moles. So then after adding 0.001 moles of HCl, how is that going to affect things? It's going to increase the moles of HClO, because that's acidic, and it's going to decrease the moles of our base. So we're going to have 0.026, because we just added 0.001, and 0.009.
This is the McPie-Woheave.
To find the new pH, we just use the same type of thing all over again. But this time, we use the new values. Base on the top here. Acid on the bottom. And when we do that, we come out with 6.94. Does this make sense? It's slightly more acidic than it was before. We added some acid, so this makes some sense. We didn't add a lot of acid, and this was a buffered solution, so we shouldn't be expecting this pH to change very much, and it didn't change very much, so it looks like life's good. All right, now question 6. We're asked to prepare this buffer solution, and they tell us the pKa of lactic acid is 3.86. We want the overall pH to be 4. So, same old story. We're going to be using that Henderson-Hasselbalch equation once again. It is the master equation of buffers. The pH that we want is 4.0. The pKa that we have is 3.86. And this entire ratio is what we're trying to solve for. Okay, so we sub in these numbers. And they're asking acid to base, so we're going to have to flip that at the end. That's okay. As long as we notice that, shouldn't be a problem. All right, fantastic. So now we're going to solve for that ratio. That's going to be 10 to the 4.0 minus 3.6. So that's going to be 10 to the 0.14 equals A minus over HA. Fantastic. And when we crunch that out, we get that ratio of 1.38. Does that make sense? Well, the pH that we're looking for is more basic than the pKa that we have. So that tells us that we do need to have more base. 1.38 is telling us that we have more base. So great. However, we were asked for acid to base, not base to acid, so we'd better flip that. So if we inverse that, it's going to be 1.38 to the negative 1, or 1 over 1.38, same deal. And we're going to come out with 0.72. Lovely. Okay, so now we're looking at part 2. Given 1 liter of this thing, and it contains this and this, how many moles of HCl can we add before the pH falls to 3? Okay, a little bit more involved here. First, big picture, how are we going to think about this? Well, what ratio would be required for pH 3? Well, as usual, we're going to use our lovely Henderson-Hasselbalch equation. We're going to have 3, the pKa has not changed, and we're solving, once again, for this ratio. Lovely, lovely. Let's clean up these notes. There we go. So we find our ratio. Oops. To be 0.138. You know what I'm going to ask here, as usual. Does this make sense? It does, because we should be expecting less base, more acid. The pH is lower than the pKa, it's more acidic, so more acid does make sense. Okay, so now what we need to do is figure out how that relates to the number of moles. Well, the number of moles of base is going to be what? It's going to be the initial number of moles of base minus the number of moles of HCl. And the number of moles of acid, what's that going to be? It's going to be the initial number of moles of acid plus the number of moles of HCl. Because if we're adding an acid, it's going to convert our base to our acid. So we're losing our base, we're gaining in our acid. And we just said that that needs to be equal to 0.138. All right, we know our initial number of moles of base here. This is in 1 liter, so concentrations are numerically the same as numbers of moles. So that's the acid there, 0.36. Again, just converting to moles, plus moles of HCl. And for the base, we're starting out with 0.50. Again, that's equal to 0.138. And after some of the least fun algebra I can possibly imagine, we are coming out with a number of moles of 0.0, oh, pardon me, not 0.0, 0.396 moles. Does this make sense? You knew I was going to ask. Well, we can't be using up all of the base, and we're not, but we should be using up most of the base, because this is getting pretty low in terms of acidity. So pretty low in terms of pH, pretty acidic. So we should be expecting our final value to be just a little bit under 0.5. We got about 0.4, so that makes perfect sense. All right, I hope that was helpful. Good luck on the rest of your studying. Starting out our thermo section with a lovely question about definitions. They tell us that we have some thermos of steeped tea, sounds wonderful. Define as many systems as you can, identify each as isolated, closed, or open. Okay, so we're going to need to make a handful of assumptions here. Let's imagine that the thermos is completely closed, like not kind of closed, not like some air can leak out, but completely closed to mass exchange. So again, no steam is getting out or anything like that. And it's also closed to energy exchange. So no heat is getting out either. In that case, the entire contents of the thermos is going to be an isolated system. It's isolated from outside. Now, each individual part of the internal section of the thermos, that is going to be a little bit more dicey, and that is going to largely just be an open system. For example, your tea leaves, that's going to be open because they're free to steep out that very delicious tea out into the water. That's the mass transfer. Also, the tea leaves, they start at room temperature, presumably, and when you pour boiling or boiling-ish water, depending on your tea, onto the tea leaves, then the tea leaves obviously change temperature. So there is energy transfer as well. We can get really, really like minuscule here and start talking like tea bag is also an open system. We can talk about the water is also going to be an open system because it is, of course, exchanging energy with all of these things. And we can say that the air in the thermos is also an open system. Air here, of course, also referring to like the water vapor that of course evaporates because this is pretty hot water. So all of these are open to each other, and all of these are isolated to the outside, again, assuming that this is like the best thermos ever. Okay, but I don't think you're likely to see a question like that on your exam. So let's proceed here. And this one I rather like. They tell us that tin is some soft metal here. Great. We have two different versions, white and gray. And they tell us that this conversion is going to has these thermodynamic parameters. Then they ask us which one is going to be stable at which temperature. My first step here is that I want to figure out which one is going to be stable at really high temperatures and which one at low temperatures. In order to do that, I'm going to think qualitatively about my Gibbs free energy equation. So what is actually favoring this reaction to go, and what is disfavoring this reaction? Well, the delta H naught, this is negative. So the enthalpy is helping to contribute to make delta G naught negative, and as a result, it's helping to make the reaction go forward. Delta S is also negative, but remember, it's got a negative sign in front of that. So if you consider that entire chunk, it's going to be positive because we're going to have negative times negative. And as a result, we would consider this first one to be contributing to reaction going, specifically going forward. And the other one is going to contribute to the reaction going backwards. So at high temperatures, the T delta S term is going to be the dominant factor, because at high temperatures, we're going to be multiplying it by a very large number. As a result, the reaction is going to be going to the left at high temperatures, and that's going to favor the white tin. Okay. So that allows us to say that white tin is going to be stable at high temperatures. That eliminates A and D, because this one is saying that white tin is these two are going to be saying that white tin is stable at low temperatures. Then we need to find out the actual temperature. In order to do that, we're going to use these parameters, and we're going to use this equation quantitatively now. Whenever you do this, you always have to watch out for the units, because delta H is pretty much always in kilojoules per mole, delta S pretty much always in joules per Kelvin mole. So I'm going to turn this all into, what do I want? I'm going to use joules, because that's probably the, I'm going to use joules. So 2.090 joules per mole. I'm not caring about significant figures here. We're looking for the temperature. We don't know that. And the delta S is negative 7.41 joules per mole Kelvin. Fantastic, but what is our delta G? Well, at a phase transition, if this thing is at equilibrium, then the reaction is not going forward and it's not going backwards. So our threshold temperature is going to be when delta G naught is equal to 0. At this point, we're just going to lovingly isolate for T. And we come out with T is 282 Kelvin. The answer choices are in degrees Celsius, so we subtract 273, and we come out with about 9 degrees Celsius. As a result, B is our best answer for this question. All right, let's continue on and get to question 3. The production of methanol by carbon dioxide, blah, 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 has an enthalpy of this. Which of the following conditions favor product formation? So which of these is going to be shifting this reaction forward? We want to think about our good friend Le Chatelier, Le Chatelier's principle. Le Chatelier's principle says that whatever you do to this equilibrium, it's going to try to go against you. So, if we're going to change the pressure, presumably by, say, changing the volume of the container, then which direction is that going to favor? High pressure is when things are pushed together a lot, and as a result, it's going to favor the fewer moles of gases. I actually like to think about it in the other way. I like to think low pressure, the gases are free to spread out as much as they want, and as a result, they're going to make tons and tons of happy gas particles. But here we've got high pressure, so we're going to squash them right down. Which side has more moles of gas? Well, they didn't actually specify this, but presumably the hydrogen is also a gas. So we have 3 moles of gas on the left, on the reactant side, we have 1 mole of gas on the product side. So high pressure favors our products. All right, we want our products being favored, so we can eliminate C and D. Now let's do the same type of thing for our heat, for our temperature. They're telling us that delta H naught is that. This reaction, therefore, is exothermic. And we can imagine heat as being a product. So if we are increasing the temperature, we're essentially increasing the concentration of a product. If we increase the concentration of the product, that's going to shift the reaction left. And that's not what we want. We want to shift this reaction to the right. Therefore, low temperature will favor products. And therefore, B is our best answer for question 3. All right, now finally, we have another quantitative one. They tell us solid aluminum chloride decomposes to give ammonia according to blah, blah, blah. So we put some sodium, did I say sodium chloride? Ammonium chloride. Ammonium chloride crystals in a container at room temperature. We take it down to P equals 0, and then we allow the equilibrium to establish. And we're asked to find the vapor pressure given our Gibbs free energy of this. So we're going to need to change this into a K somehow. We can do that using an equation from our equation sheet. K is equal to negative delta G over RT. And this is not too bad, just mind your units a little bit. Our E is going to be negative 91250, because again, I'm putting this in joules per mole, because I want it to cancel with my units on R. Great. Multiply by the temperature. So the temperature, they didn't actually specify that. They say room temperature, which we can probably take to mean 298, so that's what we'll do. And when we crunch that all out, we get a very low number, 1.01 times 10 to the negative 16. But we are not done, because we're not looking for the equilibrium constant, we're looking for the vapor pressure. Excuse me, we're looking for the total pressure. Now we know at equilibrium, we're going to have products over reactants, the partial pressure of ammonia times the partial pressure of HCl. And here, There is no denominator because we don't have anything to put there. Solids and liquids are not included in our equilibrium constants. From this reaction, this is going to be a 1-to-1 ratio, which means we can just say that our k is equal to x squared. We have the value for k, so when we solve for x, we're going to get 1.005 times 10 to the negative 8. And whenever you're using this with an equilibrium constant, this is going to be in atmospheres. Technically, yes, it's an activity, it's something divided by atmospheres, but we can convert it to atmospheres, especially if we're at low pressure, which we certainly are. Now, we do have to be a little bit careful here. These are the partial pressures, and they just asked for the pressure in the container. So this is the pressure of each species. And therefore, the total pressure is just going to be that times 2, because we have 2 species there. So it's going to be 2.02. And again, I'll be a little bit lax with sig figs. We don't really care too much about them in this course. And this is going to be our final pressure. All right, I hope that was useful. Good luck on the rest of your studying. All right, friends, it's time to talk phases. We're starting out with a real banger. We've got a temperature versus specific volume diagram and a pressure versus specific volume diagram. And we're being asked a number of qualitative questions here. They tell us to note the logarithmic scales. Okay, noted. And for question 1, and I'm going to put that in blue. A piston cylinder device contains a saturated stream of quality that. Do we remember what quality is? Quality is mass of the vapor over the total mass. So if we have a quality of 0.5, then that means that we have 50% vapor by mass. Okay. We have this pressure of 1,000 kilopascals. All right. It's heated at a constant pressure until the temperature reaches that. So I'm going to start with the first one here, just because it's the one on the left. No real strategy here. I notice that the pressures that they give me are 22, 10, 1, and 100. Now I have 1,000 kilopascals, which corresponds to 1 megapascal. So this is the line that's going to be relevant to me. They tell me that I'm starting at 50 at a quality of 50. So that means that I have half vapor and half liquid. So what do you think that's going to tell me about my specific volume? Do you think it's going to be at a maximum? Do you think it's going to be at a minimum? It's not going to be at either of those. It's going to be about halfway between these 2 points. So about halfway between these 2 points is going to be about here. And then we're going to move to the right, because we are adding heat, right? And as we add heat, more and more of this stuff is going to evaporate. So we're getting closer and closer to our vapor. Boom, now we've hit the point where everything is going to be evaporating, or evaporated. And at this point, the temperature is able to increase again. Because remember, during a phase change, the temperature doesn't change. They want it to go to 350, so we just find where 350 would be along that line. And up we go. All right, now for the one on the right here. Well, like before, we're starting at about halfway between this thing. And again, we're starting at what temperature? Or what pressure, rather. We're starting at 1 megapascal. So I kind of got to squint a little bit here, but we'll say it's like somewhere here-ish. Sure. 1 megapascal. And just like the other one, we're going to be changing our horizontal axis. Now they tell us specifically it's at that pressure. They're not saying that the pressure is changing, and in fact they say the pressure stays exactly the same. So now what we need to do is we need to expand this, increasing its specific volume, until we hit the 350 degree Celsius isotherm. Now this is actually a little bit hard to spot just because the resolution of the images that they gave us was kind of garbage here. But such is life with phase diagrams. So let's see. This is 374, and that looks to be this line here. So if this line is 374, then we should pull up just before it because we want to stop at 350. So it would be to here. Maybe even stop a little bit earlier just to make sure the grader knows that we're not actually touching that line. Okay, so that was blue, that was number 1. For number 2, superheated vapor at 10 bar. 10 bar is about, actually, we don't need to go through atmospheres. I think about bars and atmospheres as an approximation, but 10 bar is 10,000, 1,000 kilopascals. Because each bar is about an atmosphere. Each atmosphere is about 100 kilopascals, so 10 of them is going to be 1,000. And you can look at your equation sheet to make that conversion if you need to. So we've got 1,000 kilopascals, and just like before, that is 1 megapascal. Okay. We have it at 500 degrees Celsius, and it's allowed to cool at constant volume this time, until it becomes saturated water vapor. So 1 megapascal was this line here, and we're going to be starting at 500 degrees Celsius. They say it cools at constant volume, so we'd better not be changing the volume. It's going to go straight on down until, it's a bit of an uggo line, my apologies, until it hits our vapor-liquid equilibrium line. Let's be clear, I'm writing this in red. What about on this second one? Well, on the second one, again, it's 500 degrees Celsius. They give us that line. It's this kind of deal. And for this, we're starting at 500 Celsius. Yep, still 1 megapascal. So we'd better be starting, follow this line down. 1 megapascal is about here. And we need to cool it under constant volume. So again, just straight down until it gets to our liquid vapor equilibrium line. So tiny, tiny little arrow for that one. And then I'm going to do this one in black. 3. A piston cylinder device contains a compressed liquid at room temperature and an atmospheric room temperature and atmospheric pressure. Okay. So we're going to call that 101 kilopascals. Room temperature, we're in Celsius here. We're in Celsius here, so 25 degrees Celsius. Great. And it's heated at constant pressure until the entire liquid is vaporized. So that's fine. That's like normal boiling of water at room temperature, at room pressure. So this is a nice easy one, or conceptually easy. Translating it into the graphs, though, can still be a little tricky. We're starting at 25 degrees Celsius. And for 100 kilopascals, it's going to be about there. It's going to go up to 100 degrees Celsius, where we would be expecting our water to begin boiling. And then it's going to boil, 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 until all of it's completely vaporized. On this other one, we have the same type of idea. We need to find the 25 degrees Celsius isotherm. And it's not listed here. So we're going to have to kind of infer. We have 200 here, 100 here, 50 here. So 25 is going to be like somewhere around here. We don't have to be perfect. And then we are heating it at constant pressure. So we're going to follow the pressure curve here, keeping it constant. Oh, actually, what am I saying here? Starting at atmospheric pressure is going to have to be starting at about here, because our y-axis here is pressure, not temperature. I was thinking of the other graph there. Okay, so we're starting at atmospheric pressure, and again, we're going to keep it at that pressure, so it's just going to move along over here. Until it hits our vapor-liquid equilibrium line. Now, what would be the beginning behavior of this thing? So the beginning behavior is going to actually be at a lower pressure, because this is an atmospheric pressure. It is not the pressure of the the liquid vapor equilibrium. We know the vapor pressure of water is well less than 1 atmosphere, so it's going to start somewhere down here, and in fact, for 25 degrees Celsius, probably somewhere down here, again, just picking something under this temperature. So it's going to follow that thing up. It should have some curve, but its curve is going to be so small that it's hard to spot here, but it is curving a little bit like that, just a little. And then it makes its way all the way over. Fantastic. Let's proceed now and get to Q2. For this one, they give us a kind of funny question. We're told about these liquid propane sensors. They were told they have a thermochromic strip taped vertically down here. When we splash some hot water on it, it changes color from black to orange. Looks more red to me, but whatever. After a few seconds, a lower portion of the strip begins to revert back, indicating the level of liquid in the tank. Using our knowledge of heat effects and phase transitions, how does this work? So let's work this through. For one, to make sure I'm not cut off. No, good. So for 1A, let's just think about what's going on here. The hot water heats the entire strip. So that's step 1. Then the liquid propane might evaporate or vaporize a little bit. And that's going to cool the strip in contact with the vapor, or with the liquid. So let's make sure that's absolutely clear. The bottom part is going to have some liquid. Some of that is going to evaporate. When it does, that's going to cool the liquid, just like sweat cools your body when you're sweating. And as a result, the liquid is able to cool. The gas has no such phase transition available to itself. And therefore, it cools much slower. It just has to cool from, say, like the ambient temperature. Okay, so that's 1A. Now what about 1B? What's going to happen after we leave it for 5+ minutes? It's going to go back to black. All back to black. That is way too old a song to be referencing here. But it's going to go all back to black because it's just going to cool due to ambient conditions. And then 1C. Do we need a thermochromic strip, or is it safe to use our hand for this? We can totally use our hand. Save your money. I mean, provided you let it cool for like a second or two. Don't like splash boiling water on it and then slap the boiling water. But yeah, you really should be fine here. Okay, question 2. The heat required to melt ice at standard pressure, so that is 1 atmosphere, is that calculate delta H and delta U for the melting of ice at 0 degrees Celsius and standard pressure. Okay? At this temperature, they give us the density of ice and the density of water. So delta H should actually be pretty easy here, because at constant pressure, our change in the enthalpy is going to be equal to Q. So if the heat required to melt ice is that much, then that's nice and easy. Our delta H is going to be 6.010 kilojoules per mole. Okay, so now what about the delta U? Well, delta H is equal to delta U plus P delta V, or I should say delta PV. We want to be really technical here, but then we're at constant pressure. If we're at constant pressure, we can turn that into P times delta V, because no change there, so no need to take a delta. Essentially just factoring. All right, so now we want to use this thing, but what is our change in volume? Well, let's find out. They're asking us for the heat required to calculate this. Okay, so I'm imagining they want this in per mole. So what is the change of volume for 1 mole of solid to 1 mole of liquid? A little bit cut off there. There we go. Well, let's find the volume of 1 mole of solid. That's going to be the mass times the density. And what is the mass of 1 mole of water? 1 mole of water is 18.015. It's probably plenty. Grams per mole. And in fact, let's do it this way. Okay. So that's going to be 18.015 grams per mole times our density. And we're doing solid right now. So that's 916.8. Let's turn that into something that we can actually deal with. So I want, what do I want? I want that in grams per liter. So kilograms, that would be 0.9168 grams per liter. Great. Okay. Oh, wait a second. What am I doing? This volume is not right. Our density is equal to mass over volume. So our volume is equal to mass over density. There we go. I was going to say my units are not gonna work. So we've got 18.015 grams per mole over 0.9168 grams per liter. So we're going to come out with 0.0, let me get this right here, 1965 liters. And again, this is of the solid. And this is also per mole, so I can put that there if I am feeling really, really unit diligent. Okay, same thing now with the liquid. The volume of the liquid is going to be mass over density. It's going to be same mass over different density, 999.8. Oops, let's convert that into some useful units for us. 0.9998 grams per liter. All right, so our volume there is going to turn out to be 0.01802 liters. Again, that's for the volume. Okay, my goodness, so finally we can find delta V. That's going to be final minus initial. That's going to be V of the liquid minus V of the solid. That's going to be this 0.01820 liters minus 0.0 like so. And oh my goodness, that finally comes out to be negative 0.001631 liters per mole. Okay, so that's actually probably the hardest part of the question. So now we can finally sub stuff in here. Our delta U is what we're looking for. And we need to isolate for it then. So we're going to have delta U equals, let's make that really clear, delta U equals delta H minus P delta V. We already know delta H, so we're going to do that. But I am going to convert this into joules per mole. Because when I use liter and kilopascals, this is going to turn into joules. Our ambient pressure, what was it, 1? Yeah, ambient pressure, 1 atmosphere. And I want that in 101.3 kilopascals. Because again, I need that to turn into joules. I'm going to multiply that by this number here. And when I crunch that all out, I kind of wonder why I even went to all this trouble, because we come out to 6.0098 kilojoules per mole. Or maybe I'll put that in joules per mole just to make that perhaps a little easier to follow. And based on our sig figs, we would just say that that practically had no change. Does this make sense? It does. Because is there going to be a big difference in the volume of a solid and a liquid? No, not really. Like liquid to gas is a gigantic difference. It's, oh my goodness, like, more than 20 times. Just thinking one mole of water as a gas at STP is about 24 liters. So it's about 100 times. It's huge going from liquid to a gas. Whereas solid to liquid, barely any difference at all. Like, what is that, 10%, 20%, something like that? About 10%, under 10%. So that's a far cry from a difference of 100 times. Okay, great. Let's just box our answers here so that nobody's going to take off marks. And things are nice and easy to follow. Did they ask us for specific units? They did not, so we're good. Okay, now 3. I might even just take 3 down here so we can keep referencing it. So we're kind of running out of real estate. I'm just going to push this off to the side. Okay, the delta H for boiling water is that, and 100 at 100 degrees Celsius is that. Use the ideal gas law to estimate delta U. Okay, fair enough. So our delta H, as usual, is going to be H equals delta U plus delta PV. Okay, so after that, what do? They're asking us for delta U, so let's isolate for that. And like before, they are specifying a pressure, so we can say that the delta really is only going to matter for the volume. The pressure is going to stay the same. But do we really want to try to calculate a change in volume here? We don't. That would be a huge pain. So what we're going to do is instead use the idea that PV equals nRT. And what that means is that at constant pressure, delta P, or excuse me, P delta V is going to be equal to, well, do we have any change of moles? No, we're just evaporating something, so no change in moles. Do we have any change in the ideal gas constant? It's a constant, so nope. And the temperature is the thing that we're going to have a change in. So, oh, what am I saying? No, we do have a change in moles. Why? Because this is not just moles of anything. This is the ideal gas constant. This is the number of moles of gas. Let's make that really, really specific here. And if we're doing this per mole, the number of moles is going to be 1. So specifically, we're going from H2O liquid to H2O vapor or gas. So our delta N is 1. We're ending with 1 mole of gas. We started with 0 moles of gas. Okay, so we can keep going here. our delta U is equal to delta H, which they give to us at 40.88. But like usual, I'm going to convert that into joules per mole. And then we are subtracting that, oops, what am I saying? Yeah, we're subtracting that P delta V, that delta nRT, so that's going to be 1 mole times 8.314 times 100 degrees Celsius is 373 Kelvin. All right, so then we can finally come out to our final answer, which is 37. And what do we want for, I just don't want to be too weird for sig figs. I'll call that 37.78 kilojoules per mole. All right, lovely, lovely. For this next question, I am not going to talk about this one because we would need a phase diagram of like water in order to answer this question. Actually, I changed my mind here. Just grabbed a phase diagram for water, a PT diagram. So now we should be able to answer this question. They tell us it's 120 degrees Celsius. So what would we be expecting the pressure value to look like? Well, 120 degrees Celsius is here-ish. So we would trace that up. And then we would trace that to the left. And it's going to be a little bit hard to read on something like this, but it's going to be something probably, since this is a logarithmic scale, that's going to be probably about 200 kilopascals. And again, that is just from reading off of that phase diagram. All right, now let's look at the second one here. For the second one, they're asking us, they're saying something's not right here. What's the problem? The problem is this thing. What is going on here? They tell us it's single component. So what that means is when we use our degree of freedom idea, so we're going to have freedom is equal to, degrees of freedom are equal to 2 minus our number of phases plus our number of components. For the solid liquid phase, that's going to be 2 minus 2 plus 1. So there should only be 1 degree of freedom at this point. So we shouldn't be able to have multiple, what is this? Melting points at the same temperature. And we do have multiple melting points at the same temperature if we just like trace that up. So that is our problem. This would either need to go kind of like this, or maybe like this, or maybe like this, but it cannot curve back and hit a point that it already has. Onward. Okay, oh my goodness, now we're looking at some real bangers of questions here. Oh, this pressure, the pressure in a tire, depends on the temperature of the air, sure. 25 degrees Celsius, we read it at that, sure. If the internal volume of the tire is this, determine the pressure rise when the temperature increases to that. Okay, so what do we need to do here? They really should have given us a few pieces of extra information. So I'm going to put those off to the side here. Let's just write them all down while we're at it. The molecular weight of air, obviously a mixture, but on average, when you consider the entire mixture, is 28.96 grams per mole. They're later going to ask us to use the virial equation of state. So I'm going to tell you that the B of O2 is negative 15.8 centimeters cubed per mole. Okay. Okay, so, oh, and I should also tell you that this is for units of Kelvin. All right, so now let's get cracking at 1A. The internal volume is that. The temperature goes from 50, or from 25 to 50. We're going to use the idea that our good friend PV equals nRT. We're changing, what are we changing? We're changing the pressure, and we're changing the temperature. And I'm imagining we're assuming that the tire doesn't actually expand in any kind of meaningful way. So we're going to keep the volume the same, the moles of gas the same, and of course the R is the same. So we're going to isolate for P over T. And that allows us to use the ratio and use the idea that this ratio should stay the same. So P1V1 equals P2 over T2. We're asked to find the second pressure rise. So I'm going to find the second pressure first and then do a subtraction. P1 times T2 over T1. Got to put all of this in Kelvin. Our initial pressure was 210. Our T2 is going to be 323 Kelvin. Our initial temperature was room temperature, 298 Kelvin. And as a result, our P2 comes out to be 22 to 228 kilopascals. As usual, does this make sense? Yeah, it should be a little bit bigger than our existing one. If I'm being really diligent here, I would put units on that. So then our delta P, which is what they're asking us for, is P2 minus P1, and that comes out to be 18 kilopascals. So, not nothing. It's about 10%. That's substantial. Okay, now let's look at 1B. Determine the mass of the air that must be bled off in order to figure this out. Okay. So we can, I guess, find the moles of air first, or let's just kind of work through this. We want to use PV equals nRT. And for the moles of air, that is going to be the mass over the molecular weight. That's why we need that value. RT. So our mass is going to be equal to, lots of stuff to rearrange here, PV over RT times the molecular weight. That's going to be, this is at, to restore it to its initial value. Okay, so the pressure that we are looking for then is going to be, actually, I just now thought of a simpler way to do this, so let's do it that way. The pressure that we're going to use is going to be this pressure here, because that's how much we need to lose in order to get us back to our original amount. Okay, so we take our 18 kilopascals, multiply by the volume. I don't want to deal with meters cubed, so I'm going to convert that to 25 liters over RT, 8.314 times our temperature, which is still presumably on that very hot day of 50 degrees Celsius, so 323 Kelvin. And we're going to come out with 4.85 grams of air. So not a lot, not a ton. Mind you, air doesn't weigh much, so there's that too. Okay, now let's do the same thing, but we're going to find the change, let's make sure we read this question carefully. For a drop in temperature to a cold winter day, so they're asking for the pressure rise. It's probably going to be a negative pressure rise, so I'm just going to call that a pressure change. Okay, so we're going to use the same type of idea. We're going to isolate for the second pressure. Same thing. And our initial pressure was still that 210 kilopascals times the temperature 2, which is, what is it, negative 25. So that is going to be very cold then, at a temperature in Kelvin of 248 over an initial temperature of 25 Celsius, so 298. And that's going to come out to a P2 of 175 kilopascals. Our delta P then is going to be 25, 35, 35 kilopascals. And specifically, let's make sure we show this really diligently to make sure that we show the negative sign. We're going to have (175) minus the initial 210. And then we come out with negative 35 kilopascals. Okay. Oh, all that for question 1. And we've only been using the ideal gas approximation so far. Haven't even used the virial equation of state. All right. So let's do that now. The cylindrical gas tank is bigger. It's 50 liters. Is to be evacuated, then filled with oxygen gas. At that, we need 1.2 kilograms of oxygen. What pressure should we get to? We want to use the ideal version and the virial version. So for the virial version, I'm going to start with that actually, because it kind of contains the ideal one as well. We want to be using our PV over nRT is equal to 1 plus B over V. And when we isolate for P then, that's what we're looking for. We get nRT over V plus B nRT. I just want to comment on this. This thing on the left is your ideal approximation. And this thing on the right is your adjustment from ideality. Because remember, in theory, the virial equation of state is like an infinitely long sequence. We just care about the first 2 parts. Okay, so now let's sub in our numbers. For our N, we need to find out what that is. So let's just put that as an aside. We have 1.2 kilograms of O2. That is, of course, 1,200 grams of O2. Divide by the molar mass of O2. which is 32-ish. And we get 37.5 moles. Okay, so we have 37.5 moles times our R, lovely 8.314, times our temperature. We at room temperature again? Yep, we are. Our volume is 50 liters. Okay. Then we're going to be adding our B and our T. What's our B? This is in centimeters cubed per mole. We can't have it in centimeters cubed per mole because we want to be working in units of liters over here. Or at least we got to be consistent, so you can turn this to centimeters cubed if you want to. You'd have to mess with the ideal gas constant too. I'd much prefer to work in liters. So if we do that, that's going to convert to negative 0.016 liters per mole. And we're multiplying by moles, so good. This is all going to cancel out quite nicely. Times the number of moles. Kind of have to push that way off to the side, which we found to be 37.5 times R times T. Lovely, lovely. And when we crunch each of those things out, we get 1858. And that is kilopascals for the ideal. And then we come out with minus 1468 kilopascals. That seems rather high in magnitude. Note that we do have a negative sign indicating that these particles are going to pull together a little bit more than usual rather than spread apart like we saw with hydrogen in the class notes. That negative sign really does matter a lot. This is the adjustment. So our final then is going to be 390 kilopascals, which seems really low. So this deviation from ideality is really quite impactful. That's our p-virial. Let's make sure we write out all of our final answers. All right, fantastic. Whew. Okay, let's continue on. This next one is a little bit more qualitative, which is nice. Acceleration of a fluid by the rotation of an impeller blade creates a low pressure area by the eye of the pump. That thing. If the pressure is lower than the vapor pressure of the pure component, the fluid vaporizes. Hopefully this makes some sense. If the vapor pressure of something is greater than the surrounding pressure, you are going to get vaporization. Causing cavitation, and this is catastrophic. Everything breaks, it makes a lot of noise, no one's happy. Currently, water is being pumped at 25 degrees Celsius. The section pressure is 100 kilopascals. The minimum pressure in the eye is 50 kilopascals. Okay. And the discharge pressure is 150. All right. System is operating without cavitation. Life is good. So it looks something like that. A proposed modification would change the process fluid from a pure water to a 50-50 molar mixture here of water and acetone. And if we kept the same temperature and pressure profile, is this going to be a problem? So this question is essentially asking us, does the pressure of the eye, how does that relate to the vapor pressure of this 50-50 mix here. And thankfully, we don't have to think too hard here. The pressure of the eye is 50 kilopascals. And we never actually come close to that. So the maximum pressure, even at like 100%, I guess this would be acetone, would be like, what, 30 kilopascals? So we're not even coming close to that. The pressure of the eye is always greater than the vapor pressure here. So since P of the eye is greater than P of the vapor pressure, then we're fine. No problem. All right, onward. Question 6 here. We're assigned to the separation unit of a small drug production facility. Lucky us. Sounds like the pay's might be a startup. Maybe the pay's not great. A waste stream contains 60% mole propanol and 40% mole of our hexane. All right. Separation of these involves a flash operation, pressure of 1 atmosphere, and 75 degrees Celsius. So we're starting here. Let's just make sure that makes sense. Propanol versus hexane here. Okay, so I guess this is propanol, 60% propanol. Great. The TXY is plotted for 1 atmosphere. That is what we're working with, so that's good. Starting with 1. Let's write that in blue. Determine the bubble temperature and the dew temperature here. The bubble temperature and dew temperature of the waste at 1 atmosphere, and comment over the range of conditions when the flush operation is possible. Okay, so our bubble temperature and dew temperature range goes from about, what do we want to call that? 70, 72-ish to about 85. Okay. So for 1, I should put that in black or something. For 1, we're going to have 72 degrees Celsius to 85 degrees Celsius as our possible temperatures. Okay. Oh, I guess I should also specify which one is which here. The bubble point is when something is just beginning to bubble, so that is down here. And the dew point is when something is just beginning to condense, so that's going to be up here. You probably know the phases here, but just in case, we have liquid up down here, vapor up here, and liquid plus vapor, our liquid vapor equilibrium here. Okay, now let's do 2. For the normal operation, determine the composition of the liquid and vapor streams and the fraction of the system. This is all about tie lines and the lever rule. So they tell us that this is going to be at 75 degrees Celsius. So let's put ourselves right here. At 75 degrees Celsius, first of all, what is the composition of the, let's go with the vapor first. In order to do that, we trace along here toward the vapor. Once we hit the equilibrium line, we trace down. And I'm going to call that 0.35. And that's 0.35 propanol. If we wanted to, we could say 35% propanol, same deal. And therefore, it's going to be 65% hexane. Let's do the same thing with the component composition of our liquid. We trace to the left, we hit our equilibrium point. Do this, just to get that out of the way there. Equilibrium point, we trace it down. I'm going to call that 0.82 or so. Kind of squiggled a little weirdly there. Or 85%. And similar, 82%. And similarly, that's going to give me 18% hexane. Oh, that actually just reminds me, a couple pages ago, 158. I rounded that for some random reason. I did not round it in my calculations. My apologies there. Where are you? There you are. I don't know how that reminded me of that, but it did. Okay, so that is part 1 of question 2. Now we need to use the lever rule. So in order to find the amount of, what do we want to do? Let's say the fraction of vapor. Because that's what they asked us for. We're going to take, up here, the distance from the liquid to our equilibrium. So that's what I've shown in blue there. That's going to be over the distance from liquid to vapor. So that's the entire line. So when I sub in values here, the distance from liquid to equilibrium, that is this. So what is that? That's 0.82 minus 0.6. Over the total distance, which is 0.82 minus 0.35. And we come out with 0.47, or 47% vapor. Whew. Okay, so I think we've answered that entire question. Looks good. All right, not much further to go, just 2 more here. 2 more big questions, multiple parts. Question 7 here. A mixture comprised of 25% acetonitrile and 75% nitromethane is held in this tank, 60 degrees Celsius. Is the mixture a vapor, a liquid, or a 2-phase liquid and equilibrium? Assume Raoult's law applies. So what we need to do is we need to use these lovely equations to find the saturation pressures. So let's do that. For 1, we're going to have ln of P1 is equal to this whole thing. So in fact, let's do this. And that's going to be equal to 14.2724 minus 29, all of this stuff, the boring stuff, over the temperature in degrees Celsius, so 60, plus 224. And that comes out to be, we take the exponent of that, like e to the, and that comes out to be 49.45 kilopascals. And that's for acetonitrile. If we do the same thing with nitromethane, and I don't think we need to show that entire calculation again. I'm just going to skip to P2 here. Yeah, so P2 using this. It's going to be 23.42 kilopascals. Now, Raoult's law would say that if you have some mixture of these, then there's going to be, like the total vapor pressure is going to be somewhere in between those. We have an atmospheric pressure of 101 kilopascals. As a result, we would say that P atmosphere is greater than P1 or P2. So it's greater than the bigger one here. And therefore, this entire thing is not going to boil yet. Because remember, boiling happens when you have your vapor pressure over the atmospheric pressure. And we don't need to worry about any kind of like non-ideal stuff because they tell us that Raoult's law applies. So the system exists as a liquid. Lovely. For part 2, we have this mixture now, and this mixture is maintained at this pressure. We're looking for the due temperature. So the due temperature is going to probably be higher, right? Because the due temperature is when something is just starting to condense. And that means that this thing would have already had to be a gas. So it's going to definitely have to be greater. That's a bit hand-wavy because we've got different concentrations, but it's probably going to be higher. Let's work it out quantitatively. So we use our P-dew equation. We're going to have Y1 over P1 saturation. So that refers to our acetonitrile, plus Y2 over our P2 of saturation. That refers to our nitromethane. And be really, really careful with this exponent. A lot of people forget that exponent, and it's tragic. We are actually going to have to bust out these P-sats because we need this temperature. So brace yourself for some dreadful algebra. We're going to have P-dew of 70 kilopascals. Our Y1 is the amount of acetonitrile we have, so 0.55. And our P-sat is going to be E to this whole thing. So E to the 14.2724 minus 2945.47 over, and the temperature is what we're looking for, 224. Remember that exponent. I'm saying this because when I was writing solutions originally, I forgot it, and it was so tragic. 4, 5, e to the 14.2043 minus 2972.64 over, let's make sure that decimal is obvious, our temperature plus 209. All right. And when you work out all of that algebra, you come out with 80.57 degrees Celsius. And note that you should leave it in degrees Celsius. It is in degrees Celsius because that's what the data corresponds to. So that is our final answer. I'm going to shift this whole thing down just a little bit so that it's more obvious to do question 1 first. And now finally, we have this lovely phase diagram, and they ask us all sorts of wonderful questions about it. I'm going to need a little bit of extra tea for this one. We've got, what is it, nickel? No, magnesium and nickel, something like that. Yeah, magnesium, nickel. And we need to identify all line compounds. And classify them as congruent and all that stuff. So based off of where these things are, it does not look like there is going to be any 50-50 mix of nickel and magnesium. We could also maybe infer that based on like some packing structures or knowing that like magnesium and nickel are going to be really different sizes, because magnesium, of course, is on like second from the left on the periodic table. Nickel is somewhere kind of in the middle. And what that means is that there's going to be no 1-to-1 ratio of nickel and magnesium. So essentially, we are going to be stuck with like nickel to magnesium and nickel magnesium 2. So no just NiMg. Oh, they just ask us to do a lot of things here. So I'm going to kind of do all of these, A, B, and C, kind of all at once, because they're kind of all related. So we want to identify all the line compounds. So line compounds are going to be like these things. Let's talk about congruent versus incongruent melting. So congruent is when something melts into the exact same composition. So, hello everyone. It is equilibrium lesson time. Equilibrium is the state of when the forward reaction is equal to the reverse reaction. In other words, there are two opposing reactions that are both happening at the same time, but both of them are completely canceling each other out net. You can imagine this like immigration and emigration. Many people are coming in, many people are leaving, but on net, the population remains the same. When you write out an equilibrium constant, the way to do that is to take the concentrations of the products, you divide by the concentrations of the reactants, and then any stoichiometric coefficients that you have, you put those as exponents. Let's look at this example with H2 and I2 going to and returning from 2HI. We've got this lovely set of graphs here, and there are two things that I want to draw your attention to. The first one is that where this reaction ends up is completely independent of where it starts. So if I have my H2 and I2, and that's all I have in this beaker, well, the concentration starts to decrease as the reaction proceeds, and the concentration of 2HI is going to increase as the reaction proceeds. And hopefully here, There are no real surprises. But if I start out with exactly the opposite set of starting conditions, it doesn't actually make any change. Oh, little weird thing here, HI, HI, there we go. So my HI drops down. And again, this is hopefully very unsurprising to you. H2 and I2 follows along. And they wind up, despite starting in completely opposite situations, they wind up at exactly the same place. This equilibrium state I'm going to refer to as the reaction's home. No matter where the reaction is, the reaction wants to get home and stay home. I know some people like that. Anyway, the other thing that I want to point out are the stoichiometric coefficients and how they affect our concentrations. This also is hopefully not a surprise. If every time I use up some H2 and I2, I get 2 HI, then I should expect the amount of HI to change at twice the rate as the amount of H2 and I2. Here, I see the HI went up 1, 2, 3, 4, 5 units from beginning to equilibrium, and I see the HI went down 2.5 units. So of course, the reactions are going to be still abiding by those stoichiometric coefficients. Now let's look at multiple reactions. In order to add and subtract all these multiple reactions, sometimes we're going to have to change the reactions first. We might have to flip the reaction, multiply it by some number, divide it by some number, you get the picture. Well, if the equilibrium constant is product over reactants, then what happens if we flip the reaction? Well, the reactants and the products flip, right? So if we flip the reaction, all of our products and all of our reactants are also going to flip. So we flip the equilibrium constant. From here on, whatever we do to the reaction, we're going to do one level up to the equilibrium constant. So if we multiply the reaction by 3, what's going to happen to the equilibrium constant? Well, what's one level up from multiplication? It's going to be exponentiation. So if we multiply by 3 for the reaction, we raise to the third exponent for the equilibrium constant. If we divide by 4, oh, that's a little bit tricky, isn't it? Well, the easy way is to say, no, I don't want to remember another rule. Dividing by 4 is the exact same thing as multiplying by a quarter. So then, you just raise your equilibrium constant to a quarter, and you're good. What happens if we want to add these two reactions together? Well, what's one level up from adding? It's going to be multiplication. So when you multiply these things together, great, some stuff's going to cancel, you're going to come out with this as your final answer. This is just from multiplying those two things together. Please take a moment and write out the K expressions for each of these. Good luck. All right, the K expression for 1, well, let's see, products over reactants. Concentration of CO2 raised to the 3. And I do not include my liquids, and I do not include solids. So liquids and solids are not included in the equilibrium constant. Reason being, they don't really change much. Liquids are completely swamping everything, and solids are just kind of there. For the reactants, I'm going to have C3H8 and O2 to the 5. Note that it's totally fine if I'm using concentrations, even if I have gases here. Gases can also be in moles per liter, so there's no problem. You can also have Kp, which is the equilibrium constant for partial pressures, and then you just have to make sure that your partial pressures are in atmospheres, not things like kilopascals or torr. Okay, what about this last one? This last one will be CH3COO- times Na plus. And nothing as a denominator. So we just don't care about that one. It's a solid. These are our Ks. This second one is actually a specific type of K. It refers to something dissolving. We call it the KSP for the solubility product, just referring to stuff dissolving. Here we have a brief aside on the units of equilibria. This is mostly just for you unit junkies out there. You're not going to be tested on it on the exam, and it's just a little proof of, yeah, let's ignore the units, essentially. Please now try review Q2. Pause the video. Good luck. All right, the math is a little bit weird on this one. What's happened to the reaction? The reaction has flipped and divided by 2. So what do we need to do to the equilibrium constant? We need to flip it and put it to the half. When we make our equilibrium constant expression look a little bit more like our answer choices, we get 1 to the 1 to the half over k to the half, and 1 to the half is 1. So we come out with 1 over k to the half. We come out with answer choice B. All right, now please let's try review Q3. This one involves something called the reaction quotient. So if you're not sure about that, by all means, just skip to the explanation. But if you have an inkling, pause the video, give it a try. Okay, the reaction quotient is called Q, and this represents where the reaction is. So if we know K, if we know where the reaction wants to go, the reaction's home, and we know Q, where the reaction is, by comparing those two locations, we're going to be able to predict the direction that the reaction goes. Here's how it works. In the center, we put K. This is the home. This is where the reaction wants to be. In this case, our K is given to us at 4.4 times 10 to the negative 4. All right, but we don't know what the Q is, so we don't know if the Q is going to be bigger than K or smaller than K. We need to calculate Q, and we do that in the exact same way as we calculate K. This time, they're giving us stuff in atmospheres, but that's totally fine because our K is in pressures, so our Q will be in pressures. There's nothing to worry about here. Our PCl2, our partial pressure of chlorine, times our PNO2, NO to the 2 squared. That's going to be our numerator because those are our products. Then finally, we have our good friend NOCL, and that's going to be also squared. We sub in these values, and when we do, we come out with Q is equal to 0.1. Okay, so now we plot Q on this thing. Q is considerably bigger, so it's going to go on the right. In order to get home then, the reaction must go to the left, the reaction must go toward the reactants, and A is our best answer for rapid review question 3. Next up, we have Le Chatelier's principle, and this is a particular, it's not really a focus on your exam, but it still does definitely come up. sometimes within larger questions and sometimes standing alone. Le Chatelier's principle essentially says we need to relieve stress. No matter what we do to this reaction, Le Chatelier's principle says we're going to move in the direction to mitigate that stress. So what happens if someone comes in and increases the concentration of A? This would be increasing the concentration of A, of a reactant. Le Chatelier's principle then would say the reaction needs to move in such a way that the concentration of A is going to decrease. Now the reaction only has two directions it can move. It can either move forward or it can move backwards. So if we want to use up A, how are we going to do that? We're going to do that by moving the reaction forward. Now Le Chatelier's principle tries pretty hard, but it's still not going to mitigate this entire change. So A is going to decrease a little. B is also going to decrease a little. C is now going to increase because we're forming it, and we are also forming heat. Let's do one more. This time I want you to pause the video and predict how everything else will change. If we decrease the amount of C, what's going to happen? Pause the video, give it a try. All right, if we decrease the amount of C, then the reaction will move in the forward direction in order to increase the amount of C. So we're going to use up our reactants, produce our products, and again, this magnitude will not be as large as the initial stress. Next, let's talk about temperature. If they're kind enough to give us a temperature, or if they're kind enough to tell us that heat is a reactant or a product, then we can treat it just like any other reactant or product. So if I turn up the temperature in the room, the reaction will say, oh, I want to mitigate all the heat that's being formed. We're going to use up the heat in C, and we're going to produce the concentrations of A and B. A lot of times, though, they won't tell you whether heat is a reactant or a product. Instead, they're going to kind of hint at it in different ways. The first way that they can hint at it is by saying that the reaction is either exothermic or endothermic. And these are vocabulary words we're going to want to know. The way to remember this is that explosions are exothermic. What does that mean? Well, explosions give off heat, right? So heat is a product for explosions. So if the exam says that something is exothermic, then we're going to have heat being given off. The other way they might tell you this is by telling you that your delta H, your change in enthalpy, is negative. And they might just say that, or they might say something like give you an actual number. But if the number is negative, then that means that the reaction itself is losing heat. So the reaction is giving off heat. Okay. Of course, the opposite will be true if it is endothermic, and the opposite will be true if delta H is positive. The last effect that I want to discuss here is the effect of volume and pressure. So first, when we're talking pressure, we're talking specifically just the pressures of the things that are actually in the reaction. If I pump in a bunch of an inert gas like helium or argon or something like that, that's not going to affect anything. But if we change the volume, we're going to be changing all of these pressures. We need to know how changing the volume is going to affect these pressures. The easy way to think about this is to think about this as kind of a house. If you have a big house, then you can have a big family. If you have a small house, then you want not so many children. So if you have a big volume, if you increase the volume, it's going to shift to the side that has more moles of gases. If you decrease the volume, then it's going to shift toward the side with fewer moles of gases. On the left, we have 2 moles of gases. On the right, we have 1 mole of gas. So that's going to help us predict how volume is going to affect this. One last thing. Sometimes they'll ask about a catalyst. A catalyst does not actually shift the reaction. A catalyst doesn't change where you're going any more than a bike or a faster car changes where you're going. Instead, a catalyst will just get you there faster. So it doesn't change any of the Le Chatelier's principal arguments, and it doesn't change Q, and it doesn't change K. All right, we've already talked through this. Nothing else to say. Oh, other than temperature is the only thing that causes a change in K. Sometimes the exam will try to trick you. They'll be like, oh yeah, we changed the pressure, we changed the volume. Does that change K? You have to be like, no, only temperature. Only temperature changes K. Now finally, let's look at ice tables. Because ice tables are just one of those ever-present threats for the long answer sections. This tells us that we have a 1 liter flask with 1 mole and 1 mole, and they give us this equilibrium constant, and they ask what the equilibrium concentrations of all of these things are. Okay, so pause the video, give it a go. All right, so what do we have here? We will probably eventually want to use this equilibrium constant. The point, let's write that out right now. K is equal to concentration of HI squared over concentration of H2, concentration of I2. All right. These are all equilibrium concentrations, and right off the bat we run into a problem. Our problem is that we have 3 unknowns and 1 equation. So what we're going to need to do is we're going to need to relate these unknowns. Because like the concentration of H2 and I2, they're going to change by the same amount, right? If we use up one of them, we're using up the other. And if we use up one of them, we're forming 2 of these HIs. When you have this kind of problem, you can solve it by arranging your calculations in the form of an ice table. Now, there's nothing magic about an ice table. It's just a convenient way to organize our calculations. Since eventually I'm going to want to sub my values into this K expression, I want to convert to concentrations right away. Technically, you can use moles in your ice table. You can also use concentrations in your ice table. But by the time you get to your equilibrium constant, you have to have them in concentrations. So let's just do that right now. And this is dead easy. We have a 1 liter flask, so our initial concentration of H2 is going to be 1.000 molar. Our initial concentration of I2 is going to be 2.00 molar. And now we can just sub those in to our ice table. We don't have any of our product yet, so throw a big ol' 0 down there. Our ice table, the I stands for initial, C concentration, C for change, and E for equilibrium. Our concentration change, well, that's just going to be based on the stoichiometric ratios. So we're going to lose a certain amount of X, a certain amount of H2, and we'll represent that as X. We're going to lose that exact same amount of I2, and we're going to gain twice that much of 2HI. All right. So now let's write out the equilibrium concentrations. That's just going to be what you started with, plus your concentration change. So here that will be 1 minus x, 2 minus x, and 2x. All right, now we can sub these in for our expression. Fantastic. Let's do that. We're going to have 2x squared, and hold up, be really, really careful. This square goes outside of the brackets. A lot of people mess that up. All right, what else do we have? We have 1.000 minus x, 2.000 minus x. Okay, great. And we're going to sub this in. We're going to sub in our equilibrium constant, which, if I remember correctly, was 50.5. Yes. Okay, so this is a bit of a pain. Sometimes we get to use our small x approximation. Can we use that now? Absolutely not. The small x approximation can be used if the reaction barely goes forward at all. Here we have an equilibrium constant of 50.5, which means this reaction is fairly strongly product favored. So this reaction goes pretty hard. As a result, we unfortunately will have to bust out our lovely quadratic equation. We can isolate for 0 here, and we get 46.5x minus 151.5x. Oh, sorry, the first one was x squared, plus 101.0. And when we use our x equals negative b plus or minus square root b squared over 4ac, or b squared minus 4ac all over 2a, we come out with x is equal to 2.323, or 0.935. Do either of these make sense? Are either of these non-physical? This second one is non-physical. Because if we take 1 minus this, well, we're going to get a negative concentration. And negative concentrations don't make any sense. That tells us that this is the incorrect version, and that leaves us with our correct version over here. Now, life is pretty good. We're just going to solve our equilibrium concentrations. For H2, that's going to be 1.000 minus x. And when we do that, we come out with 0.065, because the x is 0.935. For I2, we get 1.065, and for HI, we get 1.870, and these are all molar. Now, if we want to, we can actually check this, because we can just sub these numbers in and make sure that they're equal to 50.5. When we do that, we come out with about 50.5. I'm getting about 51 here, but that is good enough for us. This means that, yeah, we probably did everything right. Yay! All right, if that seems like a lot, then pause this video, take a little walk, gather yourself, because I'd like you to please try rapid review question 5. Give this one a go, and I'll let you do it. All right, now we'll take it up together. But as I take this up, if you ever get to a point where you're like, oh, then by all means, pause the video and pick up where you left off. Okay, so I'm going to do an ice table. Why? Because I need some final concentrations. I need to know how these are going to relate to one another. So I'm just going to grab this. And we don't need to worry too much about the color text here. Like, what is MCP? Who cares? We just need to solve for its concentration. Methylcyclopentane, in case you're curious here. So let's solve this. Ice, ice. The initial concentrations are given to us. So kind. The change, well, we're going to be presumably losing some of this and presumably gaining some of that. And our equilibrium concentrations then look like so. Great. Then we can sub this into our Kc expression. All right, we have 0.143 is equal to MCP on the top here, 0.110 plus x over 0.200 minus x. All right, fun times. Just like before, we're going to have to use the quadratic equation. No, we won't. Excuse me. When we multiply this over, that makes it much clearer that we're not going to have to. So we have that. And in general, I don't like telling people how to do algebra because algebra, I think, is kind of an individual thing. When we solve for x, then, we come out with negative 0.0624 molar. Negative? Negative? Does that make sense? It's actually totally fine, because a negative change in concentration here does not actually correspond to any actual negative concentrations. So what this means is that this reaction is actually proceeding to the left. That's totally fine. We just kind of assumed it was going the other way, but the math told us otherwise, and this is not a problem at all. So now that we know what x is, I can just draw in my real equilibrium concentrations by subtracting off x there. So I get 0.2 minus 0.0624. And when I do that, I come out with 0.262. And I could say 4 if I wanted, but these are all to 3 sig figs. And also 0.0376. Fantastic. When I do that, I come out with answer choice B, and B is my best answer for this question. All right, that's it for this section. I hope it was super helpful, and good luck on the rest of your studying. Well, I accidentally hit stop recording, so I'm going to pick up roughly where I left off. I apologize if there is some amount of repetition. So anyway, again, congruent means that something melts into exactly the same composition as it came from. So it started at some composition, it melts, and the liquid has the exact same composition. So liquid, same composition. So I said we'd have no one-to-one ratio of this, and there are a couple ways of figuring that out. One of these ways is just by the number of these things. So like if we have 2 of these things and they're roughly spaced like so, it's going to be like you're going to have a 2-to-1 and then a 1-to-2. But there's a more systematic way that I'm going to explain here. They're kind of masking the ratios here by using mass. So what we want to do is, instead of using mass, we want to consider this in moles. All right, so how do we consider it in moles? Well, we just divide by the molar mass. So let's say at 54% nickel, That's by mass. So what is the number of, what's like the ratio, the mole ratio here? Mole of nickel. We're just going to go 54 over, and then its molar mass, which is 58-ish. We don't need to be perfect here. We come out with 0.93. Now that is just some like meaningless-ish number. The important part is that we're going to be able to take its ratio against the magnesium. So if we have 54% nickel by mass, we have 46% magnesium. And we do the same thing with magnesium. We're going to have 46 over its molar mass, which is 24.3. That's going to come out to be 1.9. So even though we have a greater mass of nickel here, we actually have more magnesium. What exactly is going to be the ratio? Well, I think it's pretty clear that we're going to have more magnesium. So we're going to do 1.9 over 0.93. And that comes out to be about 2. So therefore, we have 2 magnesium per nickel at 54%. What does that mean? It means that at that point, we have magnesium to nickel. Now, if that only kind of made sense to you, be sure to try it with this other one. Try to race me or pause the video. At, call that 82%. Nickel. The nickel is going to be 82 over 58, and that comes out to 1.42. That would correspond to 18% magnesium, 18 over 24.3, again the molar mass of magnesium, and that comes out to be 0.74. And if you take this ratio, this time I'm going to put the nickel on the top. 1.42 over 0.74 comes out to be about 2. So 2 nickels per magnesium. And therefore, we're going to have Ni2Mg. Okay, so over here, we would have my cutoff. There we go. Ni2Mg. Okay, and again, I'm kind of answering like several of these A, B's, and C's all at once. So at this nickel to magnesium, when that melts, it stays exactly as it is. So this is congruent melting. But when this thing melts, it melts into some mixture, and this is going to be incongruent melting. And if it kind of is too philosophical for you, you can always just say that if the line goes right up to the liquid, that's going to be congruent. If the line does not go right up into the liquid, then that's going to be incongruent. So we have done that and that. Determine their simplest atomic formulae. Yep, we did that. And we've identified those line compounds. Great. Eutectic and peritectic. So eutectic is when we have 2 solids and they are at equilibrium with 1 liquid. And at this point, I'm just going to label all of these phases because that's going to make answering B just so much easier. At the anytime we're kind of like in one of these sections that's at direct equilibrium with the liquid, you know we're going to have some amount of liquid here. This is our so-called like solid liquid equilibrium. So what do you think is going to be present on the very farthest magnesium side? It's going to be magnesium plus liquid. Okay, what do you think is going to be in this one? Well, at this point, it's not going to be pure magnesium anymore. Is it going to be more magnesium or is it going to be more nickel? Well, we're still leaning toward magnesium. We're still at a relatively low percent nickel. And we see that magnesium to nickel would be right here. So this is going to be magnesium to nickel and plus some liquid. Okay, now what do you think up here? Up here, we're between magnesium to nickel and nickel to magnesium, or I guess that would be like nickel, magnesium 2. So if we're between those, then we're going to have a mixture of those things. That's going to be the case here. So magnesium to nickel and magnesium, nickel 2. And up here, we're going to have some liquid phase as well. Okay, so what are we going to put up there then? Up here then is going to be a mixture of these things. So we're going to have magnesium to nickel, magnesium, nickel 2, and some liquid. Down here, this is pretty much flat up against the nickel side. So this is going to be nickel plus magnesium, nickel 2. So like as much nickel as we can get, though we can't get 100% nickel because like we still do have some magnesium here, right? So then over here, we're going to have just nickel plus liquid. And over here, we're going to have our magnesium, nickel 2. It's going to get a little too cramped, I think. Plus liquid. All right. Lovely, lovely. So I think we've labeled all of those places. Let's make that arrow just a little bit clearer. Perfect. Oh, actually, they probably wouldn't remove marks for not writing that in, but that's technically a phase that's on there, so we might as well write it. What do you think that's going to be? Well, it's not pure magnesium, but it is mostly magnesium. So it's going to be a mixture of magnesium plus magnesium to nickel. So it's very, very similar to this phase over here. That's nickel plus magnesium, nickel 2. I think of those as kind of the different sides of the same coin. Okay, so we've labeled each region with the diagram, with the states and the phase compositions. Great. Label all eutectic and peritectic points. Right. So our eutectic is when we have 2 solids and 1 liquid. 2 solids at equilibrium with 1 liquid. Okay, so do we see a eutectic or a peritectic point here? There's one over here, and I think this is the more straightforward one here. We have, like right here, we have a liquid, and it's formed by the melting of 2 solids. So right here is a eutectic point. And technically down here as well, because this phase down here is a mixture. So we have another eutectic point there. And those tend to be pretty straightforward when you see this kind of like drop like that. that is going to be a eutectic, where you get this little V. For a peritectic, that's when you have a solid and a liquid at equilibrium with, let me write that out, solid and liquid at equilibrium with a single solid. So this solid liquid, and I should also say that liquid is fine on this side as well. The point is you're going from one type of solid to another type of solid. So where do we see that we're going from one type of solid to another type of solid? Well, actually, this is making me realize that I made a typo there. There we go. So we're going from one type of solid, magnesium nickel 2, to another type of solid, magnesium 2 nickel. So this position, where we have one solid, another solid, and the liquid all at equilibrium, that is our peritectic point. So let's label that. Our peritectic point. Okay. Oh, I should also say technically the extremes would be considered congruent melting, but just like nobody ever says that in engineering. So yeah, technically, but whatever. Okay, D. Describe what happens assuming equilibrium as a system containing 35 grams of nickel and 15 grams of magnesium is cooled here. So first of all, note that that is 70% nickel by mass. So that's going to be along this line. Let's make sure that we write this out clearly. D is cooled from 1500 to 900. So starting up there, we're going to have, oh, it goes all the way down to here. So we're going to go from liquid to liquid plus magnesium nickel 2 to magnesium 2 nickel plus magnesium nickel 2. E. What happens if magnesium 2 nickel crystals are heated from 900 to 1400 Kelvin? So we're starting at 900 and magnesium 2 nickel. So magnesium 2 nickel would be starting like here and at 900. So that's this. Let's call that E. And it increases to 1400 Kelvin. That is actually really, really close here. So I would say that it reaches, starts as magnesium nickel 2, goes to a mixture of things there, but we don't actually need to form any liquid or any extra nickel here as long as we stay right along that line. So we can just form like straight up our magnesium nickel 2, we can keep that. And eventually we are going to reach our congruent melting point. And then finally, for F, describe what happens if we have 53 grams of nickel and 47. Okay, so I'm guessing that is there. So we're starting at magnesium 2 nickel. Oh no, because we're actually starting high temperature, 1400. So we go from liquid down to 900, so down to here. From liquid to liquid plus magnesium nickel 2. To this equilibrium between magnesium to nickel plus liquid at equilibrium with magnesium to nickel. It's a little ugly. Magnesium nickel 2. So essentially, like, since these are the same, you really just care about the equilibrium between those two. It's kind of like the same idea when we talked about the peritectic point. Like, we've got the liquids on both, so it's really a solid-solid conversion. Here we have a liquid-solid conversion. All right, and now the last two here. And these ones I think are a little bit nicer. We're doing some more flash calculations. So they start out with a pxy for furan and carbon tetrachloride. We have it at 30 degrees Celsius. We have pressure and xy. Okay. They tell us that we're starting with 300 millimeters of mercury, so along there, and 50-50 mix, so here. We want to find x1, x2, y1, and y2. So just like before, we're going to say this is liquid, liquid plus vapor, and vapor. So to find the amount of liquid, we just trace over. And we can call that, I don't know, 0.6 or so. And that is going to be specifically y1. Therefore, y2 is going to be 0.4. Same type of thing, tracing it over to the left and then down. We'll call that 0.22. And they'll always give you some leeway if you have to trace things like this. So oh, wait a second. Yeah, okay, I labeled these wrong. We have at low pressure, that's when we have our vapor. At high pressure, that's where we have our liquid. I was snoozing. I was thinking that was a temperature. Okay, so our x1 is going to be 0.22. Therefore, our y2, or our x2, is going to be 0.78. Fantastic. And the amount of vapor is going to be, again, you reach away from what you're looking for. So it's going to be this distance. So 0.5 minus 0.22 over the entire distance. 0.6 minus 0.22. And we come out with 0.737, or 74-ish%. Okay, same type of deal with this one here. This time we're starting at 90 degrees Celsius, and Z1 is 0.25. So we are here, we are here. Great. We have temperature on the y-axis here. So that means we're going to have liquid at low temperature, vapor at high temperature, and some kind of liquid vapor. I'll put it up here so it doesn't get in the way, in the middle. Starting with, let's start with y1. So we're going toward the vapor. We trace it down. That is, probably drew that just a little bit off there. Yeah, it's just a little bit short of 0.5 there. So we're going to call that 0.48. So that means that y1 is 0.48. Therefore, y2 is 0.52. With blue here, trace that down. And I'm going to call that, let's see, that's 0.25. So I'm going to call that 0.1. Might be a little bit bigger than 0.1, but I'll call it 0.1. Again, you got some leeway. X1 is 0.1, and therefore X2, our liquid phase, or our amount of the second component in the liquid phase, is going to be 0.9. They're asking for the liquid fraction this time. So as usual, we reach away from what we're looking for. So that's going to be 0.48 minus, what is this thing? That's given to us 0.25 over the total, 0.48 minus 0.1. And that comes out to be 0.605. Okay, what happens if instead we have Z1 at 0.75, so we're way out here, still at 90 degrees Celsius, we have all vapor. Oh my goodness, that was a ton. But I hope you got a lot out of it. As usual, remember that the post-midterm stuff is not typically the focus. So if you're having trouble, this kind of thing is really important. I would say this kind of thing is somewhat important. I'd be a little surprised if this appeared on your exam. This is pretty much the same thing as the last one we did, so lever rule, tie lines, always important. Be surprised if something like that appeared. I'd also be a little surprised if you see like the virial equation of gases. And I'd be a bit surprised about that. I wouldn't be surprised to see a weird, like a TV or a PV diagram. So most important things I would say are PV diagrams, TV diagrams, T-volume diagrams, and also tie lines and lever rules. All right, thanks so much for watching. Talk to you soon. All right, here we have a special section on a special equilibrium constant, KSP. KSP is the equilibrium constant referring to something dissolving. So here we would have calcium chloride, dissolving, forming 2+, calcium 2+, and Cl2 chlorine minus. What's going to be the Q expression for this? Pause the video, give it a try. It's going to be Q is equal to the concentration of calcium 2+ times the concentration of chloride squared. So far, that's been exactly the same as any other K. But there are a few extra tricks for KSPs that we need to be aware of. The reaction might not be at equilibrium even if the concentrations have stopped changing. So if you're feeling confident, just pause the video and give this a go. But I'm going to talk through it. They tell us the KSP of lead chloride is this. If we put 1 gram of lead chloride into here and swirl for a long time, all the solids lost, what are the concentrations of the species? So that first part is pretty easy, I think. The moles of PbCl2 are going to be the mass times the molar mass. The mass divided by the molar mass. So that's going to be 1.00 grams over the molar mass of 278.1 grams per mole. And that comes out to be 3.6 times 10 to the negative 3 moles. We're in 1 liter, So that means that our concentration of lead 2 plus is going to be 3.6 times 10 to the negative 3 molar. And our concentration of chloride, well, it's going to be twice that, right? Because for every lead chloride that dissolves, we get 1 lead 2 plus and 2 chlorides. So that's going to be 7.2 times 10 to the negative 3 molar. Okay, great. If you haven't already, I'd like you to pause the video and try to find your Q here and see how that helps us answer that second part of the question. All right, our Q is going to be concentration of lead 2 plus, concentration of Cl minus squared. In fact, I might as well write out this reaction just to make sure everything is nice and crystal clear here. We have this reacting or dissolving in water, giving us lead 2 plus aqueous and 2 Cl minus aqueous. Okay, so we sub in our values for Q. It's going to be 3.6 times 7.2. Make sure you get that square in there. You come out with 1.87 times 10 to the negative 7. What does that tell us about whether this reaction is at equilibrium? We set up our number line here. The K that they gave us was 1.7 times 10 to the negative 5. And the Q that we just calculated is down here. Therefore, the reaction wants to go right. What's stopping it? What's stopping it is that we are all out of reactant. As a result, this reaction has ceased. The concentrations aren't changing yet, but we are not at equilibrium. Once again, the reason for that is because it can't go right. So we're not at equilibrium, and not only that, we are never going to get to equilibrium. So sad. Next, let's talk about molar solubility. Molar solubility is the amount of a solid that can dissolve in water, and it's measured in moles per liter. So for this, we want to think about what the reaction is doing. And then we'll also, just like in the last example, sometimes have to take into account that you're going to have more of some ions than you will of others. So for calcium hydroxide, let's be good chemists or engineers and write our states here. As usual, if you're feeling confident, feel free to race me, or if you absolutely know all this stuff, then just skip to the next section. Okay, great. So our molar solubility then, we're going to call this S. Our S is going to be equal to, well, the amount of calcium hydroxide that dissolves is going to be equal to the amount of calcium 2 plus that we have. So that's going to be equal to calcium 2 plus. But that doesn't help us solve the rest of this question. So what we can use is we can use the KSP. KSP is going to be equal to, we probably have this one on lock, potentially OH minus, but remember, square that sucker. And now, how much calcium 2 plus are we going to have? We don't know, but we do know it'll be equal to the molar solubility, S. And we know the value of KSP is 1.3 times 10 to the negative 6. But now, how are we going to round out this equation? Well, we're going to have some kind of S and some kind of square, I guess. So I'm going to put a square up here. And what's the concentration of hydroxide? What's the concentration of hydroxide relative to the concentration of calcium 2 plus? It's going to be twice as much, right? So we can call this 2S. But here's the thing. Lots and lots of people make this mistake. They just write 2S squared. But this square applies to the entire concentration, and 2S is the entire concentration. So we've got to have the brackets around there, the parentheses around there, because the exponent does also affect the coefficient here. All right, so we come out with this equals 4S cubed. And when we isolate for S, we come out with 7.5 times 10 to the negative 5. Okay, if you haven't already, I'd like you to practice by trying the other two. Let's take a look. So for copper bromide, that's going to be a 1-to-1 reaction. That's going to make our lives considerably easier. Our KSP is 6.3 times 10 to the negative 9. And our S's are just both going to be nice vanilla S's, because we're going to have concentration of copper, concentration of bromine. They're going to have the same concentrations. And they're both in 1-to-1 with copper bromide. So when we isolate for S there, we get 6.9 times 10 to the negative 3. Nice. Not so nice. Actually, give me just 1 sec here. I'm going to pause the recording. Okay, yes, it's as I thought. These answers are switched. Sorry about that. I'm sure that was confusing. Okay, there we go. Thank goodness. So yes, I was thinking that that square root didn't seem to add up. All right. So let's look at this last one now. I'll do this one in a little bit more detail because it's definitely the hardest. We have lithium 3 phosphate. It's a solid. It's dissolving to give us 3 lithiums and a phosphate. Okay, so what is our KSP? KSP is that. That's equal to the concentration of lithium plus to the 3 times the concentration of phosphate to the 1. So which one is going to be S? The phosphate is going to be S because it's the one that's in a 1-to-1 relationship with lithium phosphate. 1-to-1 relationship right there. We can sub in numbers then. 3.2 times 10 to the negative 9 is equal to 3S. And make sure you have that cubed outside of the parentheses. And the phosphate is just an S. So we come out with an S equal to 3.3 times 10 to the negative 3 molar. All right. Now we have this last question, which is pretty tough. If you're feeling confident, again, pause the video, give it a try. Okay, this question asks us, imagine we need to completely dissolve this much nickel carbonate given this KSP. What's the minimum amount of water required to do that? So the minimum amount of water is going to be the amount of water that completely gets saturated by nickel carbonate. What does saturated mean again? Saturated means that you have as much nickel carbonate as you possibly can in that water. So what we're going to do is essentially just say, all right, what is the maximum amount of nickel carbonate, the maximum concentration of nickel carbonate that we can possibly get? That is the same as our molar solubility. So we're going to have nickel carbonate solid at equilibrium with nickel 2 plus aqueous plus carbonate 2 minus aqueous. And the same old story here. We're going to find our molar solubility. Our KSP is 1.3 times 1.36 times 10 to the negative 7. And that's going to be S squared. So our S, the maximum amount of nickel carbonate we can dissolve in 1 liter of water, is going to be 3.69 times 10 to the negative 4 molar. Okay, great. So how many moles is that going to be of nickel carbonate? So we're going to say that our initial mass over our molecular weight is going to be, we got to dissolve 0.1. Yeah, sorry, not how many moles is this going to be. How many moles is this going to be, the 0.1? We have 118.702 grams per mole. And that comes out to be 8.424 times 10 to the negative 4 moles. Okay, lovely, lovely. So that's how many we need to dissolve. And over here, this is how much dissolves per liter. So after that, we just need to find the volume required. The volume required is going to be the moles over the concentration, the moles over the max concentration, and that volume comes out to be 2.28 liters. Fantastic. Lovely, lovely. That's the end of this section. I hope it was helpful. Good luck on the rest of your studying. It's acid-base time. Let's go. We're starting out with the definition here. There are a bunch of ways to define an acid or a base, and the way that we care about the most for this course is the Bronsted-Lowry definition. For an acid, a Bronsted-Lowry acid produces H+. A Bronsted-Lowry base then does the opposite. A Bronsted-Lowry base accepts H+. So looking at this at this equilibrium here, take a second and write down which is an acid, which is a base, conjugate acid, conjugate base. I'll give you a hint. The conjugates are on the product side. Pause the video. Good luck. All right. So we've got this nitrogen here, and we might know what this ammonia normally does, but let's just make sure. Let's make sure it's doing what we think it might do. If we compare it between the reactant and the product side, we see that the ammonia has gained a proton. So if this ammonia, if this NH3 has gained a proton, then it's acting as a base. That means that its partner, the NH4+, is acting as a conjugate acid. What we mean by conjugate is that these two are paired up. It's like sibling. We say that this thing is acting as an acid because this is an equilibrium reaction. If this reaction goes to the left, then what's donating the proton? It's the conjugate acid. It's the NH4+. Okay, so then what's happening with this H2O? This H2O, we compare it with its partner, and we see that it has lost or donated a proton. As a result, we call this an acid because it's donating or producing those protons. And we have the OH- as the conjugate base. So these two are partnered and these two are partnered. This is also a good time to really knock down or lay down some of the vocab that we're going to be using in this section. We have H+ and H3O+. And we're going to treat these largely identically. If something loses an H+ in water, it pretty much always forms H3O+, so these things are pretty much the same. You might hear me refer to H+ as a proton. And the reason I do that is because, well, what is H? Hydrogen has one proton and one electron. What that means is that if it loses the electron, it's just a proton. So yeah, you'll hear me refer to this as H+ and a proton. When this proton meets up with water, it forms H3O+, which is also known as hydronium. And when you see each of these, I recommend thinking about these as acids. These are almost your definitions of acids. So whenever you see them, you want to think acidic. The other one is sodium, or is hydroxide. Now, hydroxide you've certainly seen before, especially as something like sodium hydroxide or potassium hydroxide. And goodness me, I'm giving that a plus sign. Sorry about that. So this is going to be what you think about when you think of bases. Because if you add a base to water, it's often going to form hydroxide. Now that we've got that on lock, we can proceed. And here we have a section on strong acids and bases. The important thing to know about strong acids is that they completely ionize in water. So this becomes a unidirectional arrow. That means that these products do not go back to the left. Okay, so if we have this, the H+, as said before, is going to immediately react with water, and that's going to form H3O+. And now H3O+, it's almost our definition of acidity. It is relatively reactive, it's pretty reactive, and it's pretty unstable. So this H3O+ is going to be looking to stabilize itself. It's going to be like, hey, A, do you want to get back together? And this A- is going to be like, no, I remember our time together. It was terrible. It's going to say, we are never, ever, ever getting back together. It says, we are never, ever, ever getting back together. And that's what this unidirectional arrow means. It means that once you form this thing, it's done. We're going to refer to this as the conjugate of a strong species. What does that mean? It means the unreactive partner of a strong species. So you'll hear me say that about stuff like sodium and chloride and potassium and bromide. If we know our strong acids, sodium hydroxide, potassium hydroxide, hydrochloric acid, hydrobromic acid, if we know our strong species, then we can recognize these as things that are just going to piece right out of there and not contribute to the reaction and not contribute to the pH. Our strong acids here are HCl, HCr, HI, HS, H2SO4, and nitric acid. These ones don't come up very much. And some years, they actually give you the strong acids, so make sure to check your equation sheet and your reference sheet, because they might be on there. If they're not, then I do recommend remembering at least these first three, and ideally, all 5 of these. Strong bases completely ionize in water. Same thing, unidirectional arrow, and this B+ is not getting back together. Common ones we see of those are going to be sodium hydroxide, potassium hydroxide, and these other ones don't come up very often. So those are strong. Those are where the direction is 100% to the right. But for weak acids and bases, those are going to be at equilibrium. So here we have our weak acid reacting with water, and when it does so, it's going to form the hydronium ion. Amazing, we've seen that before. And it's going to be forming a conjugate base. We have some examples of weak acids here, but for the most part, if they give you a Ka, then it's likely to be a weak acid. Kas for strong acids are just really, really high. They are well above 1. So if they give you a Ka, well, it's probably going to be like 10 to the negative 5 or something like that. It's going to be relatively small. Same idea with weak bases here. Here we have a base accepting a proton from water, and when it does so, it produces OH-, which we know to think of as basic. This refers to a Kb equation, and it's the same idea. It's how far this reaction goes in the forward direction. We have some examples here, but as usual, if you're unsure, just see if they have given you a Kb. Now, one trick that they sometimes do is they'll give you a K for a related species, for a conjugate species. And I'll tell you how to deal with that when we see the relationship between Ka, Kb, and the mystical Kw. Here we have pH and other P scales. The most important thing to remember here is right at the bottom. Whenever you see P of something, that means the negative log of that something. So if I say pH, that's going to be negative log of the concentration of H. Specifically H+, but we'll probably get close enough to figure that out. Similarly, concentration of POH is equal to negative log of the concentration of OH-. What about something that isn't a molecular species? What about something like pKa? Well, you can totally do that too. It is the negative log of the Ka. So hopefully you're getting the point. P of anything is equal to the negative log of the anything. It's very helpful to have some lines in the sand here. And thankfully, lines in the sand for acid-base are pretty straightforward. The big idea is that at pH 7, that is neutral. Now things can get a little bit confusing here because I always like to think in terms of acidity, but I also like to think in terms of numbers going up. So there's a little bit of an internal conflict in my mind here, but the idea is that pHs lower than 7 are going to be acidic. pHs higher than 7 are going to be basic. When you think acidic, you want to think low pH, and you want to think things like lemon juice or hydrochloric acid or something like that. When you think basic, you want to think higher pH, and you want to think of things like pumpkin spice lattes and iPhones. Okay, so that's great. We can relate pH and pOH to each other, and this is really, really useful. We can relate it as pH plus pOH equals 14. Now sometimes they won't give you this pKw. This pKw does depend on temperature, but if they don't give you a pKw, that's totally fine. They will give you a kW, and it will look something like this. Sometimes there'll be a few significant figures in front. And if you ever need to do that conversion from kW to pKw, how do you do it? Well, pKw is going to be equal to the negative log of the kW. That's going to be equal to negative log of 10 to the negative 14, and that comes out to be 14. Okay, let's continue on now, and let's do some of these sample calculations. We're going to put some strong species in water here, and the important thing to remember is that when you add a strong species to water, it completely dissociates. So here we have a 1 times 10 to the negative 1 molar solution of HCl. We hopefully recognize HCl as a strong acid, and that tells us that it will completely dissociate to give 1 times 10 to the negative 1 molar of hydronium ions. Great. That is written down there, and this allows us to find the pH very easily. We find the negative log of the concentration of H3O+. That's the negative log of 1 times 10 to the negative 1, and that comes out to be 1. Now, where things get a little bit trickier are when they ask you about a base. Because even though they ask you about a base, very often they're going to be asking you for a pH, not a pOH. This can be a little bit tricky because if you try to take the negative log of this concentration, if you have a base, then you're going to find the pOH, you're not going to find the pH. As long as you recognize this, dealing with it is not that hard, because we know that pH plus pOH is equal to pKw, which is 14. As a result, if you find your pOH, you can just sub it in to that equation, and you're going to be able to convert. Again, a little bit tricky. Your exam really likes testing on this. One might say that your exam is all about that base, but hopefully now you'll have no trouble. All right, so now we're going to look at the autoionization of water. Water is a little bit weird because it can act as both an acid and a base. And in fact, when two water molecules come together, they can act as both of these things. In this case, we have one of these water molecules stealing away one of these protons. As a result, we get H3O+ and OH-. Now, offhand, you probably have a good intuition that this is not a very spontaneous reaction. Otherwise, when I drink some water, I would be expecting to get both acid burnt and base burnt at the same time. So while yes, we can have a normal equilibrium describe this, the equilibrium here is going to be very far to the left. Weird. little box there, but that's all right. That's a degree sign. At 25 degrees Celsius, this K is 1 times 10 to the negative 14. And just like any other equilibrium constant, it's composed of the concentration of the products over the concentrations of reactants. But in this case, the reactants are in liquid phase, and as a result, they are not included in the equilibrium constant. When you have a neutral solution, your concentrations of both of these are equivalent. So at neutral, at 25 degrees Celsius, your amount of H3O plus is going to be equal to your amount of OH minus, and that's going to be 1 times 10 to the negative 7 molar for both of them. Now let's dig a little deeper into these equilibrium constants, because relating equilibrium with Ka and Kb and other acid things is something that your exam has really tested on historically. Ka refers to just another equilibrium reaction, but it's a very specific equilibrium reaction. A Ka is the concentration, or is the reaction of Ha, so some acid reacting with water, forming the products. So our Ka is going to be the reactants, the products over the reactants, raised to any stoichiometric coefficients, but for acid-base, it's actually pretty much always 1, so that makes life pretty easy. Just like any other Ka, or just like any other K, the K is approximately how far forward the reaction goes. So 1.8 times 10 to the negative 5 means that even though this is an acid, it's still going to, in general, favor the reactant side. Here's a lovely review question. I'd like you to please write the reaction of HNO2 with water, and I'll tell you that this is a weak acid. You might have been able to infer that by me asking you the Ka for that. Give it a go. Good luck. Okay, let's talk about it. For HNO2 with water, we're going to have HNO2 plus water. And to be really diligent here, I'm going to include my states. This is going to be an equilibrium reaction. And I'm going to get NO2 minus aqueous plus H3O plus aqueous. My acid is HNO2 because that's the thing that gave up a proton. So I would label this as an acid, and NO2 as the conjugate base. For H2O, that is going to be a base because it's picking up a proton. So it's a base, and H3O plus then is the conjugate acid. The Ka expression is going to be the same as always, concentrations of products over concentrations of reactants. And remember, don't include the water. All right, let's proceed now. And let's talk about the relationship between Ka and Kb. For every Ka, there is a related Kb. But some people are like, oh yeah, Ka is the acid, so it goes forward. Kb is the base, so it goes the reverse. But that's not true. If we look at the Ka, it's acid mixed with water. If we look at the Kb, it's base mixed with water. And as long as you remember, it's whatever you're talking about mixing with water, you're going to be in good shape. The reason some people are wrong when they say that this a Kb is the reverse of a Ka is because if we take our Ka and reverse it, we don't have a base reacting with water anymore. We have a base reacting with H3O+. So watch out for that, but if you just remember that the Ka or Kb is whatever you're talking about reacting with water, you're going to be aces. Okay, so that's what we see here. And then we come out with our base and our acid. And here, the Kb is exactly what we should be expecting. Products over reactants. This Kb is 5.5 times 10 to the negative 10. And here is a big important part. If they're feeling like the question is just a little bit too easy, they're going to add an extra step. For example, they might say, what is the pH of some amount of concentration of CH3COOH, acetic acid? And they wouldn't tell you the pKa or the Ka. They're going to say the Kb for CH3COO minus is, and then whatever it is, 5.5 times 10 to the negative 10. And hopefully it's a little bit obvious, but if you're asked to determine stuff about acetic acid, you can't just randomly use stuff from other molecules. That's not going to fly. So what you need to do is you need to use this lovely equation here. The Ka of the acid times the Kb of its partner base is going to equal this. So in this case, we have, or we're looking for Ka, we have Kb, and that's going to be equal to Kw. Okay, so if we're searching for Ka, we're going to have Ka equals Kw over Kb. We can sub in the numbers here, 10 to the negative 14 over 5.5 times 10 to the negative 10. And when we do that, we get 1.82, call it, times 10 to the negative 5. And when we look back and see the Ka for this exact thing, we see that yes, we have managed to calculate it. That equation does work. All right, let's proceed now, and let's look at the relationship between all of these things. The relationship between Ka and pKa mathematically is quite obvious, right? Whenever you have p of something, it's negative log of that thing. Okay, but what about qualitatively? As I increase the Ka, what happens to the pKa? A little bit unintuitively, at least in my opinion, the pKa is going to go down. Reason being, we've got that negative right there. So when you see a high Ka, I want you to think stronger acid. When you see a lower pKa, I want you to think stronger acid. And because when you multiply the partners together, they always give you a constant value, what that means is if you have one partner that's really strong, then of course the other partner is going to be weak because they always multiply together to get you that same value. It's a good thing siblings don't work that way, or there would be a lot of envy in the world. If we take the negative log of all this, we get, hopefully, an unsurprising equation. pKa plus pKb is equal to pKw, and at room temperature again, that's 14. Okay. So now we're looking at the aqueous solutions of weak acids and bases. Really, this is actually nothing new. This is just an ice table, but with one extra step. This question asks if we have 0.02 moles of acetic acid, everybody's favorite weak acid, and we add that to 10 mils of water, and we're given the Ka, they want to ask us, what's the pH? Now, when you see this on your exam, the first step that I want you to do is think about whether the solution should be acidic or basic. Here we've got an acid, so we'd better come up with something under 7. If not, we've probably made a mistake. The first step that I'm going to do here is calculate the concentration of acetic acid. The reason I'm going to do this is because eventually I'm going to have to use this Ka, and I'm going to need concentrations for that, so I might as well do that now. So I'm going to go C equals N over V, 0.02 over the volume, which is 0.01 liters. And I'm playing a little fast and loose with significant figures here. Wow, this is only to 1 sig fig, so I'll have to keep that in mind, I guess. And when I do this, I'm going to come out with 2 molar. Okay, to help orient us, I'm going to write out the reaction that's going on here. CH3COOH, aka CHCO. And we have water. Then we have an equilibrium reaction, and we are losing that proton from our acid to form CH3COO minus, CHCO, and H3O plus. Here, I'm going to be very diligent and write out my states. And now the initial concentration in molar, in fact, let's keep all of these in molar, shall we? The initial concentration here is going to be 2. Okay, how much water? We don't care. Because it's a liquid, it's not going to occur in the equilibrium constant, so we just YOLO that thing away. CH3COO minus, well, initially we're not starting with any of our products, so big ol' zeros there. But now we need to account for some kind of change. We don't know what that change is, so we're going to call that X. And our equilibrium concentrations then are 2 minus X, X, and X. Now there's nothing magic about an ice table, it's just a particularly nice way of organizing our calculations. And the big idea here is we want to relate the concentrations of our products and reactant. Because if we didn't relate that, then we'd have 3 different unknowns and only 1 equation, and we'd be in trouble. But now that we've related these, we have 1 equation, 1 unknown, and we're in good shape. All right, so now we're going to set up an expression for the acid dissociation constant. Okay, so the expression then is Ka equals concentrations of products over concentrations of reactants. And the entire point of that ice table was to figure those out relative to each other. So now we can plug in those equilibrium concentrations into our Ka. Now here we have a little trick. We can often ignore the X in the denominator. The reason that we can do that is because X represents how much of the reactant has been used up. Now, our Ka is relatively low, and our initial concentration is relatively high. So what happens when you have a big number minus a small number? It's going to give you about the same thing as the big number. Sometimes you'll be asked to justify this assumption. And if you need to, what you do is you compare the concentration, the initial concentration of what you're talking about, and you divide that by your equilibrium constant. In this case, that's going to be 2 over, what was it, 1.8? 1.8 times 10 to the negative 5. And when we do that, we come out with 11,111. Nope, I missed a 1 even there. 111,111. Make a wish, I guess. If this number is above the critical number, then you're going to be able to proceed with the small x approximation. Here, this number is gigantic, so it's definitely above that critical number, and we can just say that 2 minus x is good enough to call it 2. Okay, so now let's sub in these numbers and simplify the equation. The Ka is 1.8 times 10 to the negative 5, and that's equal to x squared over 2. Fantastic. Now when we calculate our x, we're going to find that it is 6.0, wrote it a little small there, 6.0 times 10 to the negative 3 molar. All right, that seems good. Oh goodness, this question's been so long. What are we even looking for? What do we even have? This x is actually telling us the concentration of H3O+. So that's pretty amazing, because that means all we need to do now is take pH equals negative log of that 6.0 times 10 to the negative 3. And when we crunch that out, we come out with 2.22. And that is our final answer. I know this question is long, but very often this is like the classic pick for a long answer acid-base question. What I'd like you to do now is please try this question, pause the video. Good luck. Okay, let's get cracking here. The pH of the solution when we have that is added to that. So same idea, I'm going to want to use my Kb, and this reaction will be NH3 plus water, my base reacting with water, goes to and returns from NH4 plus and OH minus. And just like before, everything is aqueous except for water. And I can now write out my Kb, NH4 plus, OH minus, NH3 on the bottom. And since I know I'm eventually going to want to sub stuff into there, I might as well find my initial concentration of NH3. Okay, so when I do that, C equals N over V equals 0.014 over 0.5 equals 0.028. Oh, and this is actually reminding me. I said before that I needed to round this to one significant figure, so let's do that. Pow! Remember that for pHs and pOHs, only the decimals after the figures after the decimal place are considered significant. Okay, back to this. I'm again only going to have one sig fig, but I'll do that rounding at the end. Now, ideally, I'm going to be able to skip this ice table, at least if this were a multiple choice question. For a long answer, yeah, you should show the whole thing. If you can skip it, great. If not, that's totally fine. I will still write this out in lots of detail. If you skipped it, by all means, just skip ahead a bit in the video. We're starting with 0.028 molar, and we don't care about the water, and we don't have any of the products. The change is minus x plus x plus x, and our equilibrium concentrations then are 0.028 minus x, x, and x. Subbing these values in to our Kb, what do we come out with? We get x, x, over 0.028 minus x. And that's equal to 1.78 times 10 to the negative 5. All right, so now I'm going to use my small x approximation. I'm not going to show the stuff off to the side this time. And when I do that, I come out with x is equal to 7.06 times 10 to the negative 4. This time, that's equal to the concentration of hydroxide. So when I take my negative log of 7.06 times 10 to the negative 4, and it comes out to be 3.15, do I select B? No, I don't. Because the very first thing I do when I see this question is to say, I have a base. I will cross off my acidic answer choices. And now that reminds me that I was not calculating pH, I was calculating pOH. Especially at the end of a long question, it's easy to grasp at that straw. Finally, I'm going to convert pOH plus pH is equal to 14. pH then is equal to 14 minus 3.15, and my pH is equal to 10.85. Fantastic. I would round this, I guess, to 10.9, but this is a multiple choice question, so D is my best answer here. All right, now it is titration time. We're going to start out with a strong acid, strong base titration. With a titration, you have some flask-looking thing. It's not a bad flask. And in that flask, you have the thing that you are analyzing. The thing that you are analyzing is called, appropriately, the analyte. Then you're going to be adding, oh goodness, I hope we don't miss. We're going to be adding, let's move that over, some of our other solution. This other solution is called the titrant. And this is what you are titrating with. So you start with the analyte, you add the titrant. Think alphabetical order, A comes before T, analyte comes before titrant. Now, in this situation, we have HCl being titrated with sodium hydroxide. So HCl is the analyte. We're starting out with HCl, and as a result, we see a very low pH. Makes sense? It's a strong acid. So we start out with that low pH, and we're adding base and 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 adding base until we hit the equivalence point. Now, there are some sketchy definitions of equivalence points, and I want to point out one of them here. A lot of times you'll hear that the equivalence point is when the number of moles of acid are equal to the number of moles of base. This is a terrible definition of an equivalence point. If we wanted to salvage it, it would be tricky. We might be able to do it. It's going to be when the initial number of moles of analyte are equal to the added number of moles of titrant. Now, if this seems like a long way to go to save a pretty bad definition, I am with you. So I'm going to give you a much better definition. It's simpler and it's more robust. It's when all the analyte has reacted. It's when all the analyte has reacted. So how much HCl do we have at the equivalence point? None. It's all gone. And therefore, we shouldn't be surprised when our pH for a strong acid, strong base titration is 7. We've reacted all of it. There's no residue that we care about. Now after that, if we keep adding base, then we're just going to increase the pH because we're essentially adding base to water at that point. What about for a strong base, strong acid titration? So here we're starting with sodium hydroxide, meaning our pH is going to start high. We add acid, the pH drops till we hit the equivalence point. And just like last time, the equivalence point, is at 7. And if we keep adding acid, we're essentially adding acid to water at this point. Nothing exciting there. The equivalence point can be found on the graph by finding the most steep point. Now, I would understand if you did not want to shell out the thousands of dollars that it would take to buy a pH probe to do this kind of equivalence point analysis. So instead, what most people will do is they will buy an indicator. An indicator is something that's going to change color when the pH crosses its pKa. For our purposes, though, what we need to know is that the indicator is going to change color at a specific pH region, and this gives you the endpoint. If you've done things well, then your endpoint is going to be about the same, at about the same pH as your equivalence point. Fantastic. Now let's move on to a more complicated situation, titration with a weak acid and a strong base. So weak, strong now. If we think about this tug of war, if we added equal amounts of this, should the overall pH be 7, over 7, or less than 7? Well, the base is the strong thing here, so it's going to be pulling stuff more toward its side. So at the equivalence point, we should expect a pH greater than 7. We should expect a basic pH. This starts out looking pretty much the same as what we saw before. We start out with a low pH because we're starting with an acid. Let's skip over the shaded region for a second. And then it continues on. We hit the equivalence point. Now, if we started with HA, started with all acid, what do we have at our equivalence point? We have all A minus. Do we have any HA left? Not in any kind of appreciable quantity, because our equivalence point is when we've reacted all of our analyte. After that point, you're essentially just adding sodium hydroxide to water with a little bit of weak base, but the weak base is going to be giving you like this much basicity compared to the sodium hydroxide. So it's essentially like adding sodium hydroxide to water after that point. Okay, now let's talk about this shaded region here. This shaded region is the magic of a weak, strong reaction. In this shaded region, you have similar amounts of weak acid and weak base. And when you have similar amounts of weak acid and weak base, that means that you have a buffer. Woo! A buffer is very good at resisting changes in pH. We see that this increases fairly slowly, even though we are literally dumping in a strong base there. At this very middle point, appropriately called the midpoint or the half equivalence point, we have a little bit of extra magic happening. This extra magic is that the pH that we're observing, 4.72-ish here, is actually going to be equal to the pKa of the acid that you're titrating. And I know this sounds abstract, but we're going to bring this home with an example a bit later. And for now, I just want to say that this can tell you exactly what kind of acid you're titrating. If you're like, oh shoot, I mixed up my hydrocyanic acid and my nitrous acid, and I don't know which is which, you can figure that out with a titration. The vertical range for this titration, for this buffer region, is plus or minus 1 pH unit. So if your pKa here is 4.72, then this would go up to 5.72. and drop down to 3.72. Because it's 4.72 plus or minus 1 pH unit, which admittedly is a little bit arbitrary, but you do see that it really starts shifting down a little bit more rapidly outside of that range. Let's continue on and dig a little bit into buffers a little bit more deeply. So the entire point of a buffer is to resist the change in that pH, and it does that by, instead of just you dump in some acid, you get H3O+. In a buffer, you're going to dump in some acid, and you're going to have a weak base converted to a weak acid. In other words, it's the difference between coming out with H3O+ and coming out with some kind of weak acid. So what I'd like you to do here is please fill in the rest of this ice table. This is when we're adding 0.25 moles of hydrochloric acid to 1 liter. Then I'd like you to please find the final pH for this table. Since we're starting at just pure water, our initial pH is going to be 7. Pause the video, give it a go. All right. Well, this is a strong acid, so this goes 100% to the right. We lose all of it, and we gain the same amount of H3O+ and Cl-. All right, so we end up with 0, and we end up with 0.25 of each of these. Now, frankly, we don't really care about Cl- because it doesn't affect the pH. But now, whoops, when we do our pH calculation for the final, that's going to be negative log of 0.25, and we come out with 0.6. Wow, a drop of 6.4 pH units. That's pretty substantial. What happens if we do the exact same thing with a buffer? And just before you do that, I'll give you the Henderson-Hasselbalch equation. The pH is equal to the pKa of the acid, which is given to you up here, plus the log of the concentration of the base over the concentration of the acid. So use the ice table to find those concentrations. You can sub in moles here because the volumes would cancel, and also because we said it was 1 liter, but even if it weren't, you still could. So please wrap this up. All right. So let's use this initially. Let's find the initial pH here. The initial pH is going to be 4.74 plus log of, initially, we have 0.5 of each. And when we crunch this out, we double check our calculator. What's going on? Well, if these things are the same, then we're going to get log of 1. And log of 1 is 0. And this is telling us what we've seen before. This is telling us when you have a 50-50 mix of your acid and your base, your pH is equal to your pKa. That's exactly what we saw a second ago, right up here. Okay, so that's fine, I guess. We're starting at, did I say 4.74? 4.72. Sorry if that was confusing. Now let's find our pH of the final. So the pKa is the same, 4.72. And we need these concentrations. Well, just like before, this is a strong acid, so this reaction goes 100% to the right. The change then is going to be minus 0.25 for both of these, and plus 0.25 for the products. As a result, we're going to have 0.25 for our A minus, 0 for our HCl, 0.75 for our HA, and we don't really care about chlorine, but we'll put it in there because I don't want to make it feel sad. Now, even before we do this calculation, let's generate an expectation of what it should be. We just dumped in a bunch of acid, so the pH is definitely going to be lower. It's going to be lower than 4.72. Now, we are in a buffer, so this probably won't be hugely lower, but let's find out exactly what it turns out to be. We take log of 0.25 over 0.75, and when we do that, we come out to 4.26. 4.26! This is a drop of like 0.5 units. Remember, pH is on a logarithmic scale, so a drop of 0.5 units, not huge, not nothing, but not huge, but way, way less than a drop of 6.4 units. 6.4 units is like 5 million times here. So that is a huge difference with just water, and that difference has been very well resisted by this buffer. All right, please pause the video, try rapid review, question 4. I'll tell you this is a trick question. So when you get your answer, just double check everything. All right, we're looking for a buffer. So we need a weak acid and a weak base. Strong acid, strong base, not going to do it for us. Weak base plus strong acid, maybe unclear. C, weak acid and weak base. Perfect. I pick C and continue reading. Oh, now I need to look at B again. Can I do this? Can I have a weak base and a strong acid and make a buffer? I sure can. What happens if I have 1 mole of my weak base and 0.5 moles of my strong acid? Now, you don't need to be able to come up with these numbers. These are somewhat random numbers. The idea is that I'm going to convert some, but not all, of my weak base into a weak acid. Because just like we saw with the ice tables above, this is going to give us our equilibrium concentrations of, well, let's actually do the whole thing, 0.5 minus 0.5 plus 0.5. We started with 0, and our equilibrium concentrations then are going to be 0.5, 0, and 0.5. In other words, we converted half of our weak base to a weak acid, and now we have this mix. The question does kind of hint at this possibility with the molar quantities need not be identical. So yes, we can convert some of a weak base into a weak acid to make a buffer. We saw pretty much that exact same thing, but with a weak acid and a strong base in our titration curve. So B and C are both correct, making D our best answer here. All right, I hope that was super useful. Good luck on the rest of your studying. Hello everyone, and welcome to the thermodynamics section. Now, I'm going to be frank with you. If you are pressed for time, this is probably the least important section for your final exam. So, if you are pressed for time, this is one that might be worth skipping. Here, we have our key terms. So if you think you have a good handle on this, by all means, just check out these key terms, make sure they all make sense, check out the quiz, and you're golden. If these don't make sense, or if the quiz went poorly, then that's what this is here for. We've got some basic vocab here. We've got our system and surroundings. And if you add up your system and surroundings, you get literally the entire universe. Now, of course, literally the entire universe is a hard thing to measure, especially all at one time. So we tend to approximate by closing off certain areas. We can have an open system, and that is the, of course, one that is the most open. Both matter and energy can be exchanged here. So for an open system, I would be an example of this. I can donate heat when I go outside. I donate heat to the rest of the world. It's cold. And for matter, I can intake matter, I can eat a pizza, and I can also release matter, but I won't go into too much detail on that. A closed system is similar, except it holds the matter inside of it. An example of that would be a pop can. Specifically, a closed pop can, hence the name. A closed pop can is going to not exchange matter, put it in the fridge, doesn't lose any carbonation or anything like that, but it does exchange energy because you put it in the fridge and it becomes cold. And then finally, we have our isolated system. For our isolated system, that would be an example of that would be like a closed cooler. A closed cooler. As long as it stays closed, no one is stealing your beer or anything like that. And as long as it stays closed, assuming it's a really good cooler, then the matter is going to stay inside of it. Briefly, we have the zeroth law of thermodynamics, and this one is nice and easy. The zeroth law of thermodynamics says that if we have A and B in so-called thermal equilibrium, and B and C also in thermal equilibrium, then essentially we have A and C also in thermal equilibrium. Put in slightly simpler terms, even a 5-year-old would be able to figure this one out. If A and B are the same temperature, and B and C are the same temperature, then A and C are also going to be the same temperature. Here we have the first law of thermodynamics. This idea is that we can relate the change in internal energy of a system with a change in internal energy of the surroundings. For the internal energy, or for the change of internal energy of the system, if it is positive, then we're going to have negative for the surroundings, and vice versa. I like to think of this as being able to lend money, or I'll say give money. If the system gives money, then the surroundings does the opposite. The surroundings negative gives, aka receives. And energy can be transferred as either heat or work, though that tends not to be a focus this semester. I'm not going to talk through these because, again, not so much a focus here. One thing that I will bring up, though, actually I'll bring that up in enthalpy. Changed my mind. So now let's take a look at the different types of heat. The first type of heat is sensible heat, because this is the heat that you can literally sense. If I touch this fairly warm tea, I can feel the heat being transferred to my fingers. As a result, there's going to be a change in temperature of my fingers, and perhaps less noticeably, a change in temperature of the tea as well. The amount of change in temperature that occurs depends on what's known as the heat capacity. The heat capacity, excuse me, the heat capacity is how difficult it is to change something's temperature. If you have just a straight up heat capacity, then the heat is going to be equal to your heat capacity times your change in temperature. So if we had a huge heat capacity, how much heat would it take to change this thing's temperature? It would also require a ton of heat to change this thing's temperature. So once again, the higher the heat capacity, the harder it is to change something's temperature. If you're talking straight up heat capacity, you're probably talking something like a bomb calorimeter or some kind of complicated machine. Whereas if you're talking about a pure substance like water or iron or something like that, you're going to tend to be using either specific or molar heat capacities. Specific heat capacities are per gram or per kilogram or per unit of mass. And as a result, to make the units work out, we need to be multiplying by mass. Similar idea with molar heat capacity. This is per mole. So we need to multiply by moles to eventually get something in either joules, kilojoules, whatever units of energy. Point is, it doesn't have moles in it. So here's a quick review question. Please give it a look, give it a go. Good luck. All right, there are actually a couple ways that we could do this one. We have a 35-gram hunk of rod of copper, and it's placed in 100 grams of 25 degrees Celsius water, and it says the water's temperature rises to 35 degrees Celsius. How much heat was transferred? You can actually look at this from either the copper's perspective or from the water's perspective. I'm going to look at it from the water's perspective. So my heat is going to be equal to the mass of the water, 100 grams, times its specific heat capacity, 4.184 joule per gram Kelvin, times its change in temperature. It went from 25 to 35, so that is a 10 degrees Celsius change in temperature. And when we crunch that out, then we come out with 4.18 kilojoules, or 4,184 joules. Either is fine. Now I can feel some people being a little bit wary of this unit canceling, because we're canceling Kelvin with degrees Celsius. Is that okay? It's actually totally fine as long as you're talking about changes in temperature. Because the difference between 298 Kelvin and 308 Kelvin is going to be the exact same as the difference between 25 Celsius and 35 Celsius. As a result, we can just kind of not care about that, and we come out with our correct answer. Okay, now let's dig in a little bit deeper into calorimetry here. Calorimetry is a way of figuring out heat flows, so a calorimeter is a device for measuring quantities of heat. You often have to keep in mind that the Q of reaction and the Q that you're actually measuring are going to be potentially different things, and very often are going to be negatives of each other. A lot of times people will use, like especially chemists, because chemists, they're not that great at engineering. Coffee cups are about as good as they can do. A lot of chemists will use what's known as a coffee cup calorimeter. And this is treated as a relatively isolated system. Now, of course, there could technically be some energy transfer, but it's not a lot, because like styrofoam is pretty good at holding in heat. There could also be some mass transfer. Maybe something vaporizes and some vapor escapes. So these types of things tend to be used for constant pressure processes. And in fact, they're going to be constant pressure, because if there's any pressure buildup, it just escapes. But we tend to have the same number of moles of gases on both sides of the equation, and that way we just don't really care. So again, the thermometer here is stuck in the water. And the water is not probably your system. You probably, threw some magnesium in here or something like that. It reacted. So the water is your surroundings. So if we were to just use this equation and kind of bust it out in both ways, we would have our mc delta T equals mc delta T. And if we say that the left is our system and the right is the surroundings, we have to throw a little negative on there to make everything work. Now, very often what you're going to see, if you drop some metal in here, maybe you're mixing hydrochloric acid with sodium hydroxide, whatever, you're doing some kind of reaction. A lot of the time, you're going to see the temperature increase. And here's why that negative sign is so important. if we just say that this is all the system or the reaction, then if we have an increase in temperature, if we forget about this negative sign, then we're going to be like, okay, increase in temperature, therefore the reaction gained energy. We're kind of pulling ourselves up by our own bootstraps here. If the surroundings gained energy and the system, the reaction, gained energy, where are we getting all this energy from? So clearly this can't be true. If the change in temperature is positive, then that means that the heat flow for the reaction is actually going to be negative. The reaction or the reactants are losing energy. And in chemistry, we say that losing energy is becoming more stable. Now here's an example of a couple different types of heat. We have our sensible heat, and I'm going to show that in red here. But we also have our latent heat. And this is called a heating curve. In this, we're starting with 1 mole of ice at negative 25 degrees Celsius, and we're turning it into 1 mole of steam at 125 degrees Celsius. So if we start down here at ice, we see that as we're adding heat, the temperature is increasing. But then, during the phase transition, and I know at this point you know this, during the phase transition there is no change in temperature. So all of the added heat just goes into changing the phase. That's our latent heat. Then the temperature goes up and up and up and up and up. And then for a very long time, all of the heat goes into changing the phase. What we can get out of this is that vaporization is actually going to be quite an involved process. It's going to take a lot of heat. And then finally, we can increase the temperature once again. And if we want to be a little bit more quantitative with what I described here, we would see that evaporating the liquid took 40.7 kilojoules, which is more than everything else combined. So evaporation, especially for water, really does take a lot of energy. Next, let's look at enthalpy. And this is something that I can see coming up. Enthalpy is going to be the change in internal energy plus delta PV. Now, if you have, say, constant pressure, which is a fairly common situation, then the delta doesn't need to apply to the pressure, because if you have constant pressure, there is no change in pressure. So if you have constant pressure, that can collapse down into delta H equals delta U plus P delta V. All right. And then based on our ideal gas law, this is a conversion we see relatively often. We know PV equals nRT. So what would this turn into? If, say, you have the same temperature, which again is pretty constant, especially when you're talking like pistons or phase transitions or something like that, then we can get the same type of thing. But instead of P delta V, we're going to use something on the right. We're going to use delta N RT. But wait, didn't I just say that this was mostly for phase transitions? So if there's a phase transition, why should there be a change in the moles? Well, because this is specifically the moles of gases. And as a result, if that's just the moles of gases, then if we go, say, from liquid to gas, that is, of course, going to be a change in moles of gases. Usually, you're going to see this kind of thing in some kind of reaction. So it'll be something like oh, I don't know, H2 plus O2, let's say half O2 goes to water. We'll call that a liquid. We'll call these gases. So I gave you a tricky one. What would be the delta N for this reaction? The delta N for this reaction is going to be product, so 0, minus 1.5 equals negative 1.5. So that would be our delta N there. All right, now let's look at our standard enthalpy of formation. This has a very specific definition, and it's one that we do need to know, and we need to know like a fair bit about it. Our enthalpy of formation is the enthalpy change to form 1 mole from its elements in their standard state. So it's a multi-part definition. We kind of know what enthalpy changes are because, I mean, we've defined enthalpy up there. If you're having trouble figuring out like how to internalize enthalpy changes, thinking of them as heat is like, I'd say 90% of the way there. And at constant pressure, those two things are going to be numerically equivalent. So it's not a bad way of thinking about it. So okay, we mostly got enthalpy change, potentially. We know what 1 mole is. We know what elements are. What are our standard states? Standard states are how things exist under standard conditions. 1 bar of pressure, pure solids. If it's a solution, it's 1 molar of that. But since we're talking pure elements, we're not going to have any aqueous solutions. So it's really just how we're going to find these things under atmospheric-ish conditions and at room temperature. So how are we going to find carbon in its standard state? Like if I just had some carbon sitting around my room here, what state would it be in? Well, it would be solid for sure, and it would be graphite. And I'd find it in my pencils. For sulfur, it's going to also be solid, and it's going to specifically be the rhombic form, but I'd be surprised if that were tested this year. And the nice thing about enthalpies of formation is that they're so well defined that you can just look them up in a book. You can look them up in like the CRC handbook or something like that, and there are lots of them there. In order to use them, though, you're going to take all of the enthalpies of your products and then subtract, in fact, So if you include the signs in your stoichiometric coefficients, then you add them. If you don't want to include the signs, then you subtract them. I'll go through an example in a sec, so hopefully you'll get a feel for that. But the point is, you compare the enthalpies of your products and reactants, you multiply by any stoich, and that can give you the change in enthalpy for some arbitrary reaction, which is amazing. You don't even need to go to the lab. You do want to know your standard states. So you can either think about this based on the periodic table. We've already talked about how sulfur is a weird one, how carbon's a bit of a weird one. But let me first give you just kind of the best mnemonic to remember a ton of these, which is have no fear of ice cold beer. So my amazing real-time color coding, I'm surprised that went as well as it did, tells you the standard states of all of these elements. So all of these, the have no fear of ice cold beer, I think we all know that ice cold beer is better in pairs. So all of these are going to be diatomics. And now, what are the states of these? Are these solid, liquid, gas? We probably know a bunch of these offhand, like we know oxygen, of course, we're breathing that in right now. That's going to be a gas. But almost all of these, in fact, are going to be gases. There are only two exceptions. The exception, of course, is ice. We all know ice is a solid, and that tells us that iodine, therefore, is going to be a solid under standard conditions. And beer, unless you forgot it in the freezer, beer is going to be a liquid under standard conditions, so that's great. All the rest of these are going to be gases. Okay, so now let's do an example. Let's keep the example of beer going, and let's say that I want to make methanol. Specifically, I want it in liquid form. What would the enthalpy, or what would the formation reaction look like here? Remember the definition, try to write it out. Good luck. All right, so we're making stuff from their pure substances in their standard states. That's going to be solid. If we want to flex, we can write graphite. I'd be surprised if that were tested, but who knows. Hydrogen, we know that's one of our have no fear of ice cold beer elements, so that's going to be H2. And oxygen, we're still having no fear of ice cold beer, so we continue on like so. And we balance this thing. We have 2 carbons on the right, so we'd better have 2 carbons on the left. We have 6 carbons on the right, so we'd better have 6 hydrogens on the right, so we'd better have 6 hydrogens on the left. We have 1 oxygen on the right, so we'd better have 1 oxygen on the left. But fractions are kind of ugly. Can I just multiply this whole thing by 2? No. Reason being, the enthalpy of formation is specifically to make 1 mole of your products. So don't be forming 2 moles of your products. In addition to having no fear of ice cold beer, you must also have no fear of fractions. Please, now try rapid review 2. All right, let's take a look. We want to make the reactions forming these 2 things. So CO gas, we're going to have graphite and O2 as a gas to make that work. Okay, what about CHCl3? Well, we want to make that thing. So again, we're going to have carbon as graphite. We're going to have hydrogen, which is one of our have no fear of ice cold beers. And we're going to have chlorine, which is another have no fear of ice cold beers. For the hydrogen, we're going to have a half in front, and for the chlorine, we have the wonderfully awkward 3 halves. Continuing on, we have this much octane that burns to yield that much heat. What is the molar enthalpy of combustion? Pause the video. Good luck. All right. So first, we want to find how much heat this thing had. It had that much heat, but if they're asking for the molar enthalpy is going to be the heat over the number of moles. And if they're not specifying whether something is at constant pressure or constant volume, especially if it's combustion, you know there's like a bajillion gases going around, so it's probably going to be like some kind of open thing, so it's going to be constant pressure. Though technically this should have said that. If that's what stopped you, by all means, pause the video again and keep on trucking. But I'm going to assume we're good to go. The heat was 1181 kilojoules The number of moles here for octane, 25.0 divided by 114.23 grams per mole. Lovely, lovely. And we come out with 5.40, say times 10 to the 3 kilojoules per mole. Okay. Now, what should the sign be? The surroundings are definitely going to be gaining heat, right? This is literally combustion. It's literally an explosion. So the surroundings must be gaining heat, which means the reaction itself is going to be losing heat. And I always like to think about that kind of qualitatively, because otherwise the signs are just too easy to mess up. All right, so here's the alternative version of that equation that I was waffling about before. I will say, remember to multiply by your stoichiometric coefficients when you're doing this. If you're feeling confident, you can, by all means, write this out. Just, I'm looking for the delta H of reaction for this. Just in terms of the delta H's of formation, you don't need to sub in any numbers. But I'm going to show you exactly how to do this. So we're going to have our products, delta H of formation of CO2. And we're not done with our products yet, plus delta H of formation of H2O. And make sure you have that 2 out in front. Okay, so those were our products. Now we're going to subtract off the reactants. And again, if you're adding this, then make sure that you have negatives in front of all your reactants. Okay, so we're going to have delta H of formation of CH4, lovely, plus 2 times delta H of formation of oxygen. Now, can I simplify this at all? I actually can, because one of these things has a delta H of formation equal to 0. Can you figure out which one that is? It's going to be this one on the right, because oxygen is already in its standard state. Now, I'm assuming that these are all gases, admittedly. But oxygen could certainly be in its standard state here, and as a result, if you're going to form something from its standard state to its standard state, there's no reaction happening, so of course that's not going to take any amount of energy. Okay, so enthalpy has some useful properties. It's a state function, which means it doesn't depend on how you get there. It's an extensive property, which means it depends on the extent, the amount that you have. Note that I'm being really, really strict here. Enthalpy itself is an extensive property. Enthalpy per mole, that would be an intensive property because it's dividing by the quantity. But again, strict enthalpy, just enthalpy, not enthalpy per mole, is extensive. If a reaction going in one way gives you X amount of heat, then a reaction going in the opposite way is going to require X amount of heat. And that allows us to use what's known as Hess's law, which we will see, which we will not see because it is not a focus this year. Just had to check that quickly. Thought I had removed that, so it's good that I remembered to. Next up, we have entropy. And entropy is useful. I'm guessing that you're going to see some kind of like qualitative shout out to entropy on your exam. It's the number of ways a system can rearrange itself, also known as the number of microstates. This is an equation you're not likely to have to use, but hopefully you can see here that the entropy is proportional to the number of microstates, specifically proportional to the ln of that number. So what's going to have more microstates than something else? I want you to think of like atomic or elemental yoga. If something can rearrange itself in a new way, then it's going to have more entropy. So a solid is really quite rigid, right? It's kind of locked in. But if it dissolves into, say, water, makes some aqueous solution, then it's now going to be able to move about. That's going to increase the entropy. Forming gases, gases have so much entropy because they're not only able to move about and rearrange themselves however they want, but they can also expand and contract, so hugely entropic. As a result, if you see a reaction where the number of gas molecules increase, then you are very likely seeing a reaction that is entropically favored. If we want to find the entropy of the change in entropy of some kind of phase transition, that's usually what this is used for, then we can use this lovely equation. The change in entropy is equal to the heat at constant pressure over temperature. Now note that this does have to be at a constant temperature, no changes in temperature here. And that's why it's usually used as a phase transition, because as you know, the temperature is locked during that time. Technically, it can also be used for other times when the temperature is not changing. For example, if you have like something that is so huge, we call it a thermal reservoir. If it's so huge that the temperature doesn't change, even if you like drop a hunk of molten nickel into it, then this equation would still hold quite well. The reason we care about entropy is because it's actually what decides whether a reaction goes or not. For a spontaneous process, that is to say a reaction that actually goes, the change in entropy of the universe is going to be greater than 0. In other words, this actually puts a directionality on time itself. Because the only reactions that go are the ones that increase entropy. If you ever find a reaction that's increasing the entropy of the entire universe, then that means you are literally traveling backwards in time. So the second law is a bit of a downer because it kind of tells us that we probably can't travel backwards in time. If you have a perfectly reversible situation, then your change in entropy can be equal to 0. But a perfectly reversible situation is more of a theoretical thing than it is a practical thing. So what I'd like you to do here is please circle the system that has more entropy. Good luck. All right, let's check it out. You heat something up, it's going to be able to stretch, bend, excite in more different ways. The second one is more entropic here. If you give it more space, then it's going to be able to spread out to expand. Or perhaps if you've expanded a piston, you've now vaporized more of your gas, whatever. Point is, more volume means more entropy. Gases are going to have more entropy than liquids. And same thing here. On the left side, we have 11 moles of gas. On the right side here, we have 21 moles of gas. And as a result, the right side wins here again. Our third law of thermodynamics says the only time you can have 0 entropy is when you have a perfect crystal at 0 Kelvin. A perfect crystal, of course, does not have different ways it can rearrange itself. It's perfect. It is locked exactly in as it is. At 0 Kelvin, that also means that it's going to stay there. As we see here, the entropy is going to increase with temperature. And if we're increasing this, we can have some kind of solid-solid state phase change. That's totally fine. That can be treated just like pretty much any other phase change. It's going to tend to have a pretty small difference in entropy though, because it is still just two solids. As you melt the thing, we know the temperature stays locked in, but the entropy is going to shoot right up. All of the energy that you're adding into the system at that point is being converted into entropy. And then we're increasing the temperature again until, boom, we hit boiling. And as we probably expect, based off of the enthalpy of vaporizations that we saw before, boiling is going to have a huge difference in entropy. The gases really are the rulers of entropy, so this is a big jump. You can use the same type of equation as we've seen before, where we take the stoichiometric coefficients of all of the products, add those things all up, do the same thing for the reactants, add those things all up, and you're good. Now, putting all of this together, we get our Gibbs free energy. Gibbs free energy is the punchline of thermodynamics, one of the most important ideas in all of thermodynamics. And it's the idea that these systems, they're going to want to minimize their energy. They're going to want to have a lower delta G, or a lower G. So if your delta G is negative, then the reaction goes. It's a spontaneous reaction. If it's greater than 0, then it's non-spontaneous or spontaneous in the reverse direction. And if it's equal to 0, then the reaction is at equilibrium. This is often going to explain a phase change. Phase changes are reversible, and they are at equilibrium. Or they can be reversible, they can be at equilibrium. So oftentimes you might be asked to figure out something on a phase change. If that's the case, your delta G becomes 0, and you can rearrange the other stuff. So that idea is largely from last semester. This year, they might ask you about, say, the Gibbs energy of the different phases of water. Now that we know that lowest energy is most stable, we can interpret graphs like this. Here, we see that at low temperatures, so about here to here, solids are the most stable, and as a result, we should expect our material to exist as a solid. From about here to here, they're going to exist as a liquid, because during that time, the liquid has the lowest G, and onward from there, the gas has the lowest G, or the vapor, we'll call it a vapor. And again, that is all in terms of temperature. Just like all of the others, you can use the same type of equation. Previously, we've been using V, so let's keep using V, and in that case, that would make this positive. All right, please try rapid review question 5. Good luck. All right, we want to find the amount of heat to boil some water. So we're boiling some water. They didn't say anything about a piston. Again, technically they should have said constant pressure. Again, if that's what tripped you up, then please pause the video and try it again. But assuming that's not, how are we going to solve this? We want to know the delta H. So we're actually going to use our Gibbs equation. And because this is a phase transition, this is going to be at equilibrium, and we can say that our delta G is equal to 0. So we're going to have T delta S is equal to, so I'm going to put that over here, like so. Now, if you wanted, you could also think about this in terms of the equation that we saw above, which was our QT equation. And think about heat in that way as well. You'd get essentially the exact same equation. Now, they don't give us our temperature, but we know what temperature water boils at room temperature, at sea level, blah, blah, blah. Did I say at room temperature? Sorry, at sea level, at 1 atmosphere. It's going to be boiling at 100 degrees Celsius. But this is not a change in temperature, so we'd better put 373 Kelvin. Our delta S is given to us, 118.89 joules per mole Kelvin over nothing. I'm used to using a different version of this equation. And we come out with put this in kilojoules, 44.3 kilojoules per mole. Yay! All right, we're done talking thermodynamics. I hope this was helpful. Good luck on the rest of your studying. Hello, everyone. It is phase diagram practice time. We're going to start out with some phase diagram basics. We're looking at our pressure versus temperature curve. On this curve, we have each area denoted by the most stable version of the substance. So at this temperature, at these pressures, this thing is going to be most stable as a solid. As we increase, it was meant to be increasing the temperature. As we increase the temperature, the thing is going to melt, and then if we increase it some more, it's going to vaporize. But it's also going to depend on the pressure. For example, if we have this at, say, 100 degrees Celsius, if we increase the ambient pressure, it will go from a vapor to a liquid. So being able to draw these types of arrows on a phase diagram is going to be super, super useful. There are some specific points on a PT diagram that matter a lot. We have our triple point, and our triple point is when we have 3 phases all at equilibrium with each other. On this phase diagram, there's only one of those, but in theory, we could have multiple. Our critical point is the point after which we have a supercritical fluid. And a supercritical fluid is where we cannot distinguish between our gas and our liquid phases anymore. We say the meniscus between them disappears, and those fluids often have the properties of both liquids and gases. So if we were to be asked what the phase transition of water is from this, what would it be? How would we draw our arrows? Good luck. Right, they say 100 degrees Celsius and 10 pascals. So we're starting here. And it goes to positive 100 degrees Celsius. So it travels along the x direction here. This is going from a solid to a vapor, and it's called sublimation. Next, let's look at degrees of freedom. This is often just kind of a throwaway bit in a longer question. The degrees of freedom tell you the minimum number of pieces of information required to describe a system. So if I rolled 2 dice, you could completely understand the system if you knew the 2 numbers that came up. Or if you knew this one, plus the sum of them was 6, you'd be able to fill that in, that's 1. Plus this second situation, if you add them up, this is 6, this is 1, we'd be able to figure out that's a 5. So we only need 2 pieces of information. Doesn't matter if it's these two or these two or these two. The point is we need two pieces of information, and therefore there are 3 degrees of freedom. It's 2 degrees of freedom. On your exam, the most likely place you're going to see degrees of freedom is degrees of freedom when you're talking about phases. So you have this lovely equation, 2, or F, this is your degrees of freedom, is equal to 2 minus your number of phases plus n, and n here is the number of components. And this top equation is the same thing, just using different variables. It's the type of thing you might see if you look at some other resources. So let's do some quick review here. I'll give you a first example. If we have a bucket of water, we have one component, that's the water. We have one phase, that's the liquid. So we're going to have, let's do it in this way actually. We're going to have 2 minus the number of phases, 1, plus the number of components, 1. So we're going to come out with 2. A bucket of water has 2 degrees of freedom, and hopefully this makes sense. If we think about liquid water, and we think about the phase diagram we saw just a couple minutes ago, we'd see that we could adjust the temperature and we can adjust the phase. I'll just flip back here. Here, we can adjust the temperature, adjust temperature and pressure. And we can do that without changing the component. Even if we're like right up against potentially a melting point or a boiling point, we can still change both of these things. We can change one like that. We can change something like this, all to avoid changing the phase. So now what I'd like you to do is please try the rest of these. Good luck. All right, let's talk through them. We have a block of ice in a bucket of water. So our degrees of freedom are going to be 2 minus pi plus n. And in fact, I'm just going to copy that. So that's going to be 2 minus the block of ice in liquid water. Both of these are different phases, right? So we're going to have 2 minus 2 plus our number of components. It's just a liquid, so that's 1. So that's going to come out to be 1. Okay, for this next one, we have a sealed container containing ice, liquid water, and water vapor. That's going to be 2 minus the number of phases, 3 phases here, solid, liquid, gas, plus the number of components, just water. So we come out with 0 degrees of freedom. We are at the triple point. We cannot change we cannot change the temperature or the pressure because this is completely determined. A sealed chamber containing 2 materials of gas, liquid, and solid. Okay, so same idea here. 2 minus the number of phases. We have 3 phases. But now we have 2 components, and as a result, we have 1 degree of freedom. Now let's look at how these different phases relate to energy. And if you did the thermodynamics section, then you've already seen this before, and feel free to skip ahead. So for Gibbs energy, we see that we have the lowest Gibbs energy at low temperatures for a solid. And what that tells us is that a solid tends to be the most stable at very low temperatures. Hopefully this makes sense. At low temperatures, we have deposition or we have freezing. For intermediate temperatures, we're going to have the lowest G, or the most stable state, being liquid. And for very high temperatures, we're going to have it being the vapor phase. Speaking of the vapor phase, we can have our vapor at equilibrium with liquid. So as you increase the pressure, as you compress something, as you compress a vapor, it's going to turn into a liquid. Or as you expand the volume of something, it's going to become a gas. This line, wow, that was a really good trace. This line follows Antoine's equation, which looks like that. Sometimes you'll see this as a ln instead, so just be mindful of the version that they give you. And you can use this to find the saturation pressure at different temperatures. B is just some experimentally determined thing, nothing too fancy there. C is also an experimentally determined thing. And the important part here is that you're going to be adding your C plus your T, and you just need to make sure that these are in the same units. They're always going to specify. So they'd say something like -32, and then they'll say like in Kelvin or something like that. And if that's the case, then you just need to make sure that you are adding the stuff in Kelvin. But sometimes they do this in degrees Celsius, so just be a little careful of that. All right. Based on what we're seeing here, there are two ways to condense a gas. So let's imagine that we have 100 degrees Celsius at 10 kilopascals. Now, how are you going to do this isobarically and isothermally? Isobaric means same pressure. Isothermal means same temperature. Well, if you want to condense this isobarically without changing the pressure, what you're going to have to do is turn down the temperature. And if you want to do this isothermally, you're going to have to turn up the pressure. Those are good qualitative things to know. Few pieces of vocab here. Superheating a vapor. This is when you have a vapor at a temperature or it doesn't need to be much, but needs to be greater than the saturation temperature. So if you have something here and you increase its temperature, you have now superheated it. And all that means is that it's no longer at your vapor-liquid equilibrium because it's 100% gas. And it's not going to change based on any small changes. Same idea with a subcooled liquid. This is a liquid at a temperature under Tsat. So if we're sitting over here, and we push this to the left, we cool it down, then this thing is now supercooled. We have one more, and that is a compressed liquid. That's a liquid at greater pressure than Psat. How would you draw that on here? If you want to compress something, you're of course going to increase its pressure. And now we are at a higher pressure than the vapor-liquid equilibrium line. So this is our compressed liquid. Okay, we're done our little aside here. Back to phase diagrams. Now we're looking at TV diagrams. Temperature and specific volume. The specific volume is the volume per kilogram. So what I want you to do is I want you to think about this as we are starting out with 20 degrees Celsius water. And we have this piston, and this piston has 1 atmosphere pushing against it. So it's just against atmosphere. So at 20 degrees Celsius, that stuff is practically all liquid water, right? But what happens when we begin to heat it? That's either fire or Bart Simpson's hair. So we're heating this thing up, and very quickly, the temperature goes up like really fast, right? At least fast compared to what we're about to see. And if you did the thermodynamics section, you saw this kind of heating curve idea, and so hopefully this looks kind of familiar to you. So the temperature goes up quite rapidly, but once it's at 100 degrees Celsius, at least pushing against 1 atmosphere, it's kind of stuck there. It's stuck at 100 degrees Celsius because now this stuff is going to boil. And as it boils, all of the temperature, all of the new heat, rather, is not going to change the temperature. All of the new heat is now going to be absorbed by the latent vaporization enthalpy. In other words, all the heat is going into changing the phase. So during that time, the specific volume is dramatically increasing because we're converting liquid to vapor. Once we've converted all of our liquid to vapor, that's at 0.4 here, then there's no more phase change to be had, and therefore we can get back to our sensible heat, and the temperature is going to go on up. And what happens to the specific volume as it goes on up? Well, we can approximate that using our PV equals nRT. If our temperature is going up, our volume is going to go up, and that's what we see here. So all of that was if we were pushing against 1 atmosphere. What about if we were to push against something harder? So this is about 1 atmosphere. What would happen if we had a higher pressure? Well, would the liquid begin to vaporize earlier or later? Let's check our phase diagram. If we had a higher pressure than atmosphere, say up here, 1 megapascal, we see that the boiling point of water is now considerably higher. My lines are a little bit janky there, but somewhere on the order of 150-ish, maybe 160-ish degrees Celsius. So we should expect to need to get to a higher temperature before this stuff starts boiling. That's exactly what we see. Now we do see a little bit of horizontal movement here, and hopefully that makes sense. Because I think we know that water is going to contract as it gets to a relatively low temperature. And as it gets to a higher temperature, even if it stays as liquid water, it's still going to expand. So there is going to be a small difference in specific volume, and that really is a small difference. I mean, note that this is a log scale, so that's pretty small. But eventually, we will get it up to the appropriate boiling point, and it's going to be a little bit bigger than it was at 100 degrees Celsius, but not by a lot, not too much bigger in terms of specific volume. And now we're going to be able to evaporate this thing. And we're going to vaporize. This is again our liquid to gas. Vaporize until it's all gas. And then this just takes off. Because then all of the heat that we're adding is going to a sensible heat. It's going to temperature. Okay. So do we expect all of our vapor to, let's say we had 1 mole of vapor, do we expect that 1 mole of vapor to be as big as a lower pressure? We shouldn't, right? If we have PV equals nRT, if we are going to increase the pressure, what's that going to do to the volume? The volume is going to go down. So if we're calling this like one, I guess this is per kilogram, 1 kilogram of water at 1 megapascal is of course going to be much more compressed, much smaller than 1 kilogram of water at 100 kilopascals. And all of these same arguments are going to apply at 10 megapascals. So our saturated liquid, our liquid water is going to be more compressed, but that allows it to get to a bigger specific volume before it actually starts evaporating. So as we saw before, as the pressure goes up, this thing can take more and more and more temperature before it begins to evaporate. But eventually, you see this horizontal line getting smaller and smaller and smaller. Eventually, we're going to hit a point where this horizontal line ceases to exist. What does that mean? It means that the difference between our liquid gas, and our gas, the difference between our liquid and our gas stops being observable. We have a name for that. The name for that is our critical point. So once we get up to that particular pressure and that particular temperature and that particular, in this case, volume too, because that's going to be all related, that's when we get to our critical point. So we know above that is going to be our supercritical fluid. Now you can imagine that we could do this at 500 kilopascals and 5 megapascals, and we could kind of fill this in, and we'd keep seeing these shrinking and shrinking lines, right? And if we did that again over here, it would be here-ish. If we did it again here, it would be here-ish. And eventually, we hopefully start to see a pattern. Like this kind of goes off down there, doesn't it? And when we do enough of these things, we find that it's not actually a straight line. It actually kind of curves out just a little bit. And that is our saturated vapor line. We can say those vocabulary words, but let's just make sure that we actually understand what we're talking about. We started as a liquid. We had a liquid-gas equilibrium here. And once we get to here, that's when we have all gas. So a saturated vapor line, that means that you have 100% gas, but you are right at equilibrium with your liquid. So if you compact it a little bit, boom, it's going to go over to a liquid. If you drop the temperature a little bit, boom, it's going to go down into a liquid, or at least part of it will be, right? This is at equilibrium. Going to have both here. Over here, we've got our superheated region, because these things, I should say over here, we've got our superheated region, because these things are not going to immediately go to our liquid. And over here, we have our compressed liquid region, because these things aren't immediately going to go into our gas. This also introduces the idea of the quality region, which I think is a weird piece of vocabulary. But quality is kind of a funny name. It's the mass of your saturated vapor over your total mass. And you can either write the total mass as just m total, or the sum of your mass of your vapor and your mass of the liquid. You can also, instead of using the masses, use these finding molar volumes. And this is beginning to knock on the door of the lever rule. This is a special case of the lever rule. If it looks familiar to you, then that would hopefully be why. So once again, the quality region here is this entire section. But where is the quality going to be the greatest? It's going to be the greatest when you have practically all gas. So it's going to be the greatest along your saturated vapor line. Okay, we're done with our unary phase diagrams. Now let's look at our binary ones. These are where we have multiple species. So let's imagine that we have two different species here, both alike in dignity. And let's say we have a 50-50 mix of each. At very low temperatures, we should expect this to all be a liquid, right? At very high temperatures, we should expect it all to be a vapor. So as we are slowly increasing the temperature, we're watching it, and whoa! Our first bubble forms. When our first bubble forms, that is called the bubble point. So it's when the liquid just starts to vaporize. Not all of it, but just your very first bubble. So you have like a negligible amount of vapor at that point. On the flip side, let's consider if we start at a very high temperature, and if we go downward here, we started at a high temperature, so it's all vapor, and then boom, your first tiny little droplet forms. And when your first tiny little droplet forms, engineers like to think of this as like dew on grass. So we call this your dew point. And of course, both your bubble points and your dew points are going to depend on the 2 or 3 or 5 or 10 different species that you have in this thing. So you have an entire curve here for your dew and bubble points. Along this x-axis, we have the mole fraction of component 1, and sometimes we're going to call that, say, Z1. Z1 means the total. You consider your vapor, you consider your liquid, and when you consider everything together, Z1 is the mole fraction of 1. So here, the mole fraction of 1 is 0.5, meaning that you have 50% of component 1. Up here, this is your mole fraction of component 2, so this is going to be Z2. Let's just lock this down. If you went here, what would be Z1 and what would be Z2? Okay, so I'm saying that this is like probably 0.25. Z1 is going to be 0.25. Z2 is going to be the complement of that, 0.75, because these two are always going to add up to 0.75. Now, based on this diagram, can you figure out which component is more volatile? Which component will evaporate more easily? It's going to be component 2, because that's the one that is going to boil at a lower temperature. So component 1, when we have 100% component 1, this thing is going to boil at its maximum point, which is telling us that component 1 is more difficult to boil. Now, I've been using Z's a bunch, but we've probably also seen X's and Y's, so let's define those. X1 would be the mole fraction, or I'll just say fraction. Sometimes they use mass fractions. Fraction of component 1 in the liquid phase. And Y1 is going to be the same type of thing, but instead of liquid, it's going to be gas. Vapor. Okay, so how can we find these things out? They ask us at 0.5 of component 1, 0.4 of component 1, so we're going to call that about here. Look about right. I guess that line's probably it. So 0.4, component 1. What is the composition of the vapor? So let's use this example isotherm. Let's use this temperature. At example isotherm. So what we do here is we say if we want to know how much vapor is being, if we want to know how much of each component we have in the vapor, we take our point, we just trace this toward the vapor part. We know this entire thing is the vapor part, right? So we trace it toward the vapor, and we then trace it back down, and we would see that about 0.2 of our component 1 is going to be in that vapor. How would we write that out? We would say the vapor at this point, so that's a y1, is going to be equal to 0.2. How much of y2 do we have in there? We're going to have 0.8. Because as usual, these need to add up to 1. Now, does this make sense? Should we have more of component 2 than component 1 in our vapor? Yes, absolutely. Because remember, component 2 is the thing that boils or vaporizes more easily. So if we're looking at our vapor, we should pretty much always have more component 2 than we have component 1. This last question says at 0.25 for the isotherm, how much vapor do we have, again, at that sample equilibrium? So we trace this thing up, boom, 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 at that sample isotherm, rather. How much vapor are we going to have? This introduces the lever rule. And for the lever rule, what you do is you take what you're looking for, the vapor, and you go away from it. You go away over total. So what does that look like here? Here, we want to know how much of the vapor we have. So the vapor phase is over here, the liquid phase is over here. We're going to go away from the vapor phase. So our away is going to be 0.4 minus 0.25. And our total is going to be this entire span. Our total is going to be 0.4, and we'll call that, what did we call that before? 0.2? 0.2. And when we do that, we find that the amount of our vapor is going to be 0.75, which is the same as saying 75%. So then how much liquid would we have? It would be the complement of that, so it would be 0.25 or 25%. Okay, so that is the lever rule, and I've defined it in a more rigorous way here, but most of the time you're going to be using it on an actual graph, in which case you do, I recommend at least, thinking about it more visually. And this can be used in lots of different situations. It can be used for masses. It can be used for specific volumes. It can be used for components. The entire idea is that anything that goes along the x-axis you can use it with the lever rule. So if you had two phases, liquid and vapor, and we had some mass here on our x-axis, what would be the representative equations for these? So if you wanted the mass of the vapor, then you have to go away from the vapor. And they want this, oh yeah, they want this in terms of molar volumes. So let's turn this into molar volumes. So you're going to go away from the vapor. That's going to be V tot minus V, and it's going to be liquid because it's away from vapor, over V tot. And sometimes you'll also see V tot as I'm just going to say V tot. You might also see it as like V vapor minus V liquid. But that's the same thing as we were saying here. So total span is the same as going from the liquid to the vapor. If we wanted this for liquid instead, it's going to be V tot minus V of, again, you go away from what you're looking for. So your vapor over V tot. All right. And this is, I should say, like your molar volumes. All right, so now let's look at a p mole fraction diagram. First of all, let's just get comfortable with this kind of thing. Let's start to interpret this thing. So what is going to be up here? Is this going to be vapor or liquid or what? Well, at high pressure, things get compressed and they become liquids. At lower pressure, they're going to be vapors. And then in here, you have liquid plus vapor. So now let's read through these questions. We have half benzene, so we are here-ish, at 0.6 bar. So we are like right here. What happens as we raise the pressure? So we start out as a vapor, and then it becomes a liquid and a vapor, and then it becomes a liquid. When the pressure meets the lower curve, it is currently all vapor, and it's just beginning to turn what? It's just beginning to turn into a liquid, so here this would be your dew point. And that's why it's so important to not try to memorize like dew is on top or bubble is on the bottom, because for a P versus XY diagram, it's going to be different than a T versus XY diagram. So whenever you see a new figure like this, just do take a second and think like, what's going to be here at high pressure, what's going to be at low pressure, and that's going to really help out. When the pressure is raised slightly more, what's going to happen? We're going to get some liquid formation. And what is going to be the fraction of benzene in this new phase? So I'm going to be really specific here, and I'm going to say at the dew point. So we'll do our tiling here. We go up. What's going to be the mole fraction in this new phase? So that's going to be, the new phase is the liquid phase. For the tie line, we draw that across. We drop it down. And I'd call that high 0.2s. So about 0.28 or so. As the pressure increases, what happens to the quantity of the liquid? Well, it's becoming closer and closer to all liquid, so it's going to increase. When the pressure goes between the two lines, so we'll say like right in there, how does that affect the mole fraction of the benzene in the vapor? There are a couple ways of thinking about this. The first way is thinking that if we do this all the way down here, then this would be, like this vapor would be practically all toluene, right? Because it's almost no benzene. And when we get all the way up here, then this thing is going to be all benzene. As we travel up this way. Well, no need to be so abstract about it. Let's just do a couple tests. At, what is this here? Call that 1.1. So right at the very beginning, we decided it was 0.28 fraction of benzene. What is it up here? Well, up here, we see that it is now, call that 0.4, 0.42, 0.43. We're going to call it 0.43. So what happened as we increase the pressure? We are going to increase the mole fraction of benzene in the vapor phase. All right, we've got some more examples here. If you're feeling confident, pause the video. So what do we have here? Temperature versus XY. And we have acetone and ethyl acetate. And on our x-axis here, we have acetone. What's the boiling point of pure acetone at atmospheric pressure? Atmospheric pressure is the red series. Pure acetone is on the far right, so it looks like something over here. We'll call that we'll just call it 330. It's good enough. Just a little under 330. Okay. Over what span will a 30% ethyl acetate mixture? So 30% ethyl acetate means 70% acetone. Be really careful. Sometimes they will specify something other than the x-axis. Will exist in a vapor-liquid equilibrium at 53 kilopascals. So 53 kilopascals is this bluish one, navy blue, something like that. And if it's 70% acetone, the temperature range is going to be from here to here. So we trace these over. I'll call that 316 to 319. All right. So now, like we already have all of the things that we need to do those dreaded flash calculations. Flash calculations are going to involve some Z coming in, and then it's going to get separated into X and Y. And that's pretty much exactly what we did in our previous example, like way up here. This was a flash calculation in disguise. For flash calculations, you are going to find the amount of liquid or vapor at a vapor-liquid equilibrium. You're going to use the lever rule, though you generally want to just make sure that first you are actually at a vapor-liquid equilibrium. If it's all vapor, or if it's all liquid, then nothing is being separated. But that tends not to make for a very interesting question, so they tend not to ask you that kind of thing. We've got an example here, and this one is all written out. So we have this initial condition, and it's a mixture of vapor and liquid, and we want to find the proportions of compositions in this thing. And they tell us we have lots of this, 300 kilomoles of this thing. What is the number of moles of composition in each phase? So we're going to say from here, what's going to be, where's our gas? Where is our liquid? At high temperatures, we're going to have that vapor. Low temperatures, we're going to have that liquid. So if we want to find how much we have in the vapor phase, take our x and we go, as usual, away over total. So away from vapor, that's toward the liquid. That's 0.4 to 0.2. Our total spans all the way across. We'll call that 0.4 to 0.1, just to keep our lives easy. And as a result, we're going to come out with 2 over 3, or 0.67. So I really do encourage you to use this kind of graphical thought, because otherwise you wind up just like writing and writing and writing and writing, and that's no fun. Oh, and did they actually ask us for the number of moles? They do actually ask us for the number of moles. So we have 2/3 of the number of moles in the vapor phase. If we have 300 kilomoles, that means our number of moles in the vapor phase is going to be equal to 200 kilomoles. The moles in the liquid phase, the complement, 100 kilomoles. Life's good. Okay. Oh, actually, just 1 second here. They also ask us for the composition of each phase. Okay, fine, we can do that too. We're rock stars, we're unstoppable. So what is our composition in our vapor? We're going to call that Y1. Our composition is, we go to our vapor, 0.1 of our whatever this is, B. And therefore, component 2, we can call this B, I guess, Y, B, and Y of the other thing, call it YA, is going to be the complement. It's going to be 0.9 of A. So then, they want the number of moles of this. So if we have, let's see, that was vapor. So if we have 10%, write this out in words because otherwise it can get confusing. 10% of vapor is B. We have 200 kilomoles of our vapor. Therefore, we're going to have 20 kilomoles of B as a vapor. And therefore, 180 kilomoles of A as a vapor. If you haven't already, do the same thing for the liquid. For the liquid, we know we have 100 kilomoles of that thing. And in the liquid phase, it is 40% B. Therefore, we're going to have 40 kilomoles of B in liquid phase, and therefore 60 kilomoles of A in vapor phase, in liquid phase. Seems like we have more of A in both of these. Does that make sense? Yeah, sure. Because we only have 20% of B in general, so we should be expecting to have considerably more A than B anyway. All right, now let's look at Raoult's law. Raoult's law is pretty simple if you're dealing with just one component. It tells us that the partial pressure, or the vapor pressure, of component I is going to be equal to the total pressure times the mole fraction of I. Sometimes you'll also see this as yi. That's totally fine too. So let's just do a little intuition check here. Let's imagine we're salting our pasta. And salt is non-volatile, so it's not going to contribute to any vapor pressures. Give this a read, give it a go. Good luck. All right. So to find the vapor pressure of this whole thing, because the salt's not going to contribute, so the vapor pressure of just the water is going to be the entire vapor pressure. We have the total vapor pressure from the pure thing, the pure component, times the mole fraction. It's a losing battle with this multiplication sign. Times the mole fraction, which was 0.9. I'll call that xi. The vapor pressure is 0.7 atmospheres times 0.9, and we come out with 0.63 atmospheres. But what would happen if we mixed a volatile solute with another volatile solute? Then we'd need to combine the vapor pressure from component 1 and the vapor pressure from component 2. All right, so please try this one. Good luck. All right, our total vapor pressure is going to be equal to, let's do the water first. We had 80% water, 0.8 times its vapor pressure of 0.7. We're going to add our vapor pressure of, or our mole fraction of ethanol, 0.2, times its vapor pressure of the pure solution, of the pure solvent, pure liquid at this temperature, which is 1.2 atmospheres. And when we add those together, we get a lovely 0.8 atmospheres. All right, now we have a brief intermission for gases. For ideal gases, we have all of these assumptions, but frankly, there are only 3 assumptions that really matter for us. Those assumptions are 1, 4, and 5. Assuming that gas particles have no volume is going to be a reasonably good assumption if the volume between particles is way bigger than the volume of each particle. So it's not going to behave ideally at very high pressures, because then all of the molecules are just like shoulder to shoulder, and the volume that each particle takes up becomes significant. What about the intermolecular forces? Intermolecular forces are assumed not to occur in ideal gases. So when is that likely to be true? That's likely to be true at high temperatures. Because at high temperatures, these particles are just zooming past each other, and they're not going to have any time to interact in any kind of significant way. So if we dial down the temperature, then they're going to be able to have those intermolecular interactions, and therefore they're going to be able to actually violate the ideal gas assumptions. So 1 and 4 are kind of similar because they give us these ideas of when a gas is going to behave ideally. Number 5 is sometimes tested separately, though I'd be surprised to see it on your exam this year. That's the idea that gas particles span a distribution of speeds. That's point 1. If I take 2 nitrogen molecules from the air, they were probably going at different speeds because they span a distribution of speeds. So some xenon atoms are going this fast, about 250. Some xenon atoms are going this fast, about 100 meters per second. It's a distribution. But it's not actually their speeds that is determined by temperature. Their kinetic energy that's determined by temperature. So we're going to have 1/2 mv squared in relationship with temperature. And as a result, if we have a really heavy atom, then in order to keep this true, we would have to decrease, not quite that much, we'd have to decrease the velocity. And that's why we see xenon, which is a heavier atom, is on average, or on mode technically, traveling at about 180 meters per second. Whereas argon is moving so fast, don't blink, it'll be gone. It'll be traveling at about 350. And the reason for that is because it's lighter. In order to take these things into account, for this course, we want to use the virial equation of state. And this is the equation that you have on your equation sheet. Be a little bit careful with the units. When they give you something like B, just make sure it's in the right units. Sometimes they'll give it to you in like something per cubic centimeter or something, and you need it in liters or whatever. So just really watch the units there. Sometimes also they'll ask you for molar values of things, in which case the N is just going to be 1. And let's use these qualitatively to figure out exactly what's going on with this graph. Pause the video, give it a try. So why does CH4 have a greater Z than H at higher pressures? Let's find those two things. CH4 is this. Why does it have a greater Z at higher pressures? Well, at high pressures, which of the two relevant ideal gas assumptions are we violating? At high pressures, remember, they're like shoulder to shoulder, and CH4 is just bigger. It has a greater molecular volume. And as a result, the space that it takes up is going to impact things more. Why does CH4 have a lower Z at lower pressures? Why is it way down here compared to hydrogen way up here? Well, because CH4 is going to clump together a little bit more at low pressures. It's going to do that because the intermolecular forces are bigger for CH4. And then why does the NH3 curve stop? It stops because it is no longer a gas. What happened to it? NH3 has intermolecular forces. In fact, it has hydrogen bonding. It condensed, became a liquid. And obviously, our ideal gas approximations are not going to apply to liquids. All right, in this final part, we just have a few pieces of discussion about binary phase diagrams involving solids. So we have a few different situations here. Here we have a partially miscible mixture, which means that some of the solids are able to actually dissolve in other solids. Based on that, we have what's known as a solidus and a liquidus line. Our liquidus line is where we have liquid with bits of solid starting to fuse into it. So a liquidus line is going to look like that and like so. Our solidus line is going to be the lower line here across there. Okay, so great. Now this solid, is this pure K? No, it's not. Because even at like this point, it's only 90% K. What do we have? We have joium and Ke-ium. So we have 90% K, which means this solid is a mix of J and K. For real. That can only happen because these things are at least partially miscible. You're able to dissolve one solid in another solid. When you have a pretty even mix, though, at that point it's kind of like hard to dissolve one completely in the other. So you get this mixture of solids. And then over here, same idea. We have solid 1, which is not all J. It's going to be mostly J. So on the right, this solid is mostly K. This one over here is mostly K. Not all, but mostly. And then when this thing begins to melt, it essentially gets something that is comparable to a, let's see, we're going up in temperature, to a bubble line. So it's not called a bubble line, it's different, but it's going to be kind of similar. Because that is where liquid just begins to form. And then when liquid finishes forming, we get to our straight liquid. Similarly, this top line, this liquidus line, is somewhat similar to a dew line. So some parallels here. This point here is called a eutectic point. And more on a eutectic point a bit later. Okay, so great. We've labeled a bunch of these things now. That's lovely. Oh, sorry, yeah, 1 second. I labeled the solidus line totally wrong. The solidus line is the parallel to the bubble point, not that bottom line. Let's fix that. Lovely. Okay. So this eutectic point. So the eutectic point tells us about this eutectic line. This eutectic line right here. And this is going through a multi-equilibrium point where we have all 3 phases at equilibrium. If we want, we can use the lever rule to find a bunch of these things. We can find like maximum solubility, but I'd be kind of surprised to see that that asked about on your exam. Okay, so now we're looking at an example with some solid mixtures. What are the phases and compositions at this? Well, first, let's write these things in. Our top part is going to be a liquid. Down here, we're going to have solid 1 plus solid 2. We're going to have solid 1 plus a liquid here, because it's going from a solid 1 to the liquid. Solid 2 plus a liquid here. And life is good. I think at this point we've probably done lever rules to death, but I did write out a big ol' solution here. So I'll just give you kind of the highlights here. We can use the lever rule to find the moles of solid 1 at 364.86. Moles of solid 2, solid 1, not silicon. Solid 1 at 135.14. These are both in kilomoles. The moles of K in solid, 36.5 kilomoles. Moles of J in solid. This is in solid 1. In solid 1, we're 328.37. Kilomoles. Oh, you can see why these can get kind of long. And in fact, I'm just going to screenshot stuff and throw it up here because I think that's probably more helpful. And I think we've already just done this absolutely to death. So I don't think it's necessary to do it all in this different situation. Oh, okay. Let's continue on, because we definitely want to see these completely immiscible sections. So what if we had J that's completely insoluble in K? So the maximum solubility is going to be 0. There's going to be no place where a solid region has any of J in it. So if we look at solid 2 here, we never have any amount of J in solid 2. So at this point, what do we have? Even though we only have this tiny little bit of J, the J is going to be 100% in the liquid phase. What about here? Even if we only have a tiny little bit of J, all the J is going to be in the solid 1 phase. None of the J is going to be in the solid 2 phase. So the solid S2 phase is pure K in this case. If they're completely insoluble in each other, then it's going to look like this. And note that even if we have the smallest amount of K, we cannot have just S1, because S1 is just J. S2 is just K. We can kind of figure that out because, like, on the far right here, we have mostly S2, and any amount of J is in the liquid. Over here, we have mostly S1, and any amount of K is in the liquid. All right. Let's continue on. And I just want to emphasize our eutectic versus peritectic points. So we've seen a eutectic point here. A eutectic point is when you go straight from a liquid to solids. And I want to make it clear that for a eutectic point, we have, oh, 1 second, this is a little funky. All right, for the eutectic point, it's going to go from a liquid to solid, normally solids. But for a peritectic point, and sometimes you'll be asked to find these two. First of all, realistically, how do we find them? They're little bumps. So a eutectic is like a complete valley here. Whereas a peritectic is going to be bump. You got that little bump there, so that is going to be your peritectic. A peritectic is when you're at equilibrium between a precipitated phase and a liquid to form a new solid phase. So we've got our A plus liquid here. We've got our A4B plus liquid here. So we formed a new solid phase between them. There's still liquid involved, but that's totally fine. The important part is that our A and AB are at equilibrium with each other. Let's label that for the notes. All right. Whew. Congratulations on making it through all this. I hope it has been helpful. Good luck on the rest of your studying.